Good morning. My name is Debbie Hersman, and it is my privilege to serve as the chairman of the National Transportation Safety Board. I would like to take a moment to introduce my colleagues, Vice Chairman Christopher Hart and Member Robert Sumwalt. Welcome to the boardroom of the National Transportation Safety Board. Under the 1976 Government in the Sunshine Act, multi-member federal agencies conduct much of their business in the open sessions. Therefore, board meetings are often called sunshine meetings. While the public is invited to observe the meeting, only the board members and the NTSB staff will participate in today's discussion. Before we begin, I'd like to make a few comments. First, on behalf of the board, I would like to thank all of the individuals and organizations who helped in this accident investigation. These include representatives of local, state, and federal agencies, first responders, police personnel, service organizations, and so many others. In particular, I would like to recognize the South Carolina Highway Patrol and the Federal Bureau of Investigations. Both of these organizations were instrumental in helping our team of investigators secure the accident site, preserve evidence, and document the accident scene. I would like to also recognize the National Highway Traffic Safety Administration for providing tire and peer review information, which was integral to our analysis. I'd also like to mention the Columbia Metropolitan Airport management team. They provided their full support to our investigators while we were on scene, allowing them to complete the work that was needed, even though that meant closing down the Columbia Airport for the better part of a day. We recognize that there were a lot of travelers, airport personnel, and many in the community that were inconvenienced that day, and we were grateful for their patience and cooperation. To all the groups that were involved, thank you very much for your assistance. It was invaluable. I'd like to also acknowledge the family members and friends of those who lost loved ones or who were seriously injured in this accident, some of whom are watching our proceedings today. On behalf of the men and women at the Safety Board, please accept our condolences and concerns for your loss and all that you have endured since this accident. It is in response to this accident and your loss that we meet today to determine the probable cause of this accident and consider safety recommendations so that accidents like this one do not happen again. While the board members are the ones who are sitting here on the dais today, it is our staff who have done the work to produce this comprehensive report. On behalf of the other board members, I thank you for your hard work, your dedication, and not only for conducting a thorough and comprehensive investigation, but for promptly issuing 6 safety recommendations in advance of the completion of the final report. Thank you for producing this excellent report for our consideration today. There are many important issues that we'll discuss. Before proceeding to the report, I'd like to take a moment to briefly mention a public forum that the Safety Board is going to be conducting next month, May 18th to 20th. The forum, entitled Professionalism in Aviation, is intended to raise public awareness of industry best practices and to promote an open discussion between the Safety Board and invited panelists on the importance of developing and ensuring excellence in pilot and air traffic controller performance. Panelists will be drawn from industry, government agencies, labor, academia, and professional associations, and we will explore a variety of topics. I believe that forums like this one are important exercises to create additional opportunities to improve the safety of our aviation system, and I invite you to join us. A few weeks ago, the staff submitted notation 8061A, a draft report for the board's consideration. On September 19, 2008, a Bombardier Learjet Model 60, operated by Global Exec Aviation and destined for Van Nuys, California, overran runway 11 at Columbia Metropolitan Airport during a rejected takeoff. Tragically, 4 people were killed: the captain, the first officer, and 2 passengers, and 2 other passengers were seriously injured. The board members have had the intervening weeks to study these documents. While we might have met with staff individually to discuss the draft, today is the first opportunity for all of the board members to meet together and discuss the issues contained in the draft report. During this meeting, the board members will hear staff presentations addressing the primary issues identified in the investigation, issues that may include inadequate tire maintenance, pilot performance and training, crew resource management, aircraft design and certification, and the monitoring and ongoing risk assessment of safety critical systems. While these issues are specific to this accident, they also have a broader implications for aviation safety. The board members will solicit staff comments and explanations on many points. Once we have discussed the draft report, we will then consider the conclusions, the probable cause, and the recommendations proposed by the staff. Sometimes all or part of the draft conclusion, probable cause, or recommendation is revised or rejected by the board members. This is because these are the actual deliberations over the documents. That's the purpose of the Sunshine Act, to provide the public a window into our decision-making process. Approximately 30 minutes after this meeting, copies of abstracts containing the conclusions, probable cause, and recommendations approved by the board can be obtained from the board's Public Affairs Office and will be placed on the web. I'd like to thank my colleagues for their input to the staff that resulted in improvements to the product before it was brought to the board today, and thank the staff for their willingness to work with the members to address all of their concerns. Dr. Meyer, would you please introduce the staff and begin the presentations?
Yes, ma'am. Good morning. Sitting to my right is John DeLisi, Deputy Director of the Office of Aviation Safety. Next to John is Bill English, the investigator in charge. Then Bob Swaim, Airworthiness. Dr. Catherine Wilson, Human Factors. And at the end of the table, Captain David Tu, Operations. Behind Dave is Jeff Marcus, Safety Recommendation Specialist. And to Jeff's left is Tim Birch, Aircraft Performance. Kathy Gagne, Report Writer. Joe Colley from our Office of Research and Engineering, the Director of that office. And next to Joe is Tom Zoller, Executive Officer, and Gary Halbert, General Counsel. Bill English has the first presentation.
Thank you, David. Thank you, Madam Chairman. As mentioned, on September 19th, 2008, about 11:53 p.m. Eastern Daylight Time, a Bombardier Learjet 60, operated by Global Exec Aviation, overran runway 11 during a rejected takeoff from Columbia Metropolitan Airport, South Carolina. The captain, the first officer, and 2 passengers were killed. 2 other passengers were seriously injured. The non-scheduled domestic passenger flight to Van Nuys, California, was operated under 14 Code of Federal Regulations, Part 135. Visual meteorological conditions prevailed, and an instrument flight rules flight plan was filed. The airplane had arrived with just the crew about 40 minutes prior to the departure, loaded the passengers in fuel, and was ready for departure just prior to midnight. The airplane had a long taxi from the northeast ramp, and they back taxied the entire length of runway 11 for takeoff. During the taxi, the crew performed the required pre-takeoff briefing. However, the captain, who was the pilot flying, misstated some criteria for a rejected takeoff, or RTO, and did not fully correct the briefing. The initial takeoff roll was normal, and the first officer made the required airspeed call at 136 knots. Less than 2 seconds later, the cockpit voice recorder recorded a loud rumbling sound. In response to the sound, the first officer called to continue the takeoff. However, the captain first reduced power and then wavered, briefly reapplying power, then quickly reducing power, and committing to the high-speed RTO. Both crew members expressed confusion over the source of the sound, and the captain affirmed the rejected takeoff. Investigators found numerous rubber fragments of all 4 main landing gear tires along the runway, and an NTSB performance study aligned the fragments with the loud sound heard in the cockpit, indicating that the tires all failed during the takeoff roll. And follow-up examination of the tire fragments revealed that all 4 main tires were underinflated to far below allowable pressures. The airplane began decelerating, although stopping capability was compromised due to the tire failures. About 4 to 5 seconds after the captain confirmed the RTO, the tire fragments damaged wiring harnesses along the gear struts, causing the airplane logic to switch to air mode. Since reverser deployment in the air can be dangerous, the thrust reversers automatically stowed. However, the engine power command was not affected, resulting in high forward thrust in spite of the captain commanding full reverse. This issue was the subject of recommendations A0955 through 60 issued during this investigation, and we will have details in a later presentation. The airplane exited the runway and safety area at high speed, eventually impacting a roadway berm and catching fire. This overhead view of the airport shows a simplified version of the significant events. The loud sound was recorded about 1.5 seconds after reaching V1 speed. The airplane reached a maximum speed of about 144 knots and decreased to about 130 knots during the initial RTO. A comment by the captain is consistent with noting the reversers deployed and they were committed to the high-speed rejected takeoff. CVR evidence and systems examination indicate that thrust reversers stowed while the throttle controls were commanding high power, resulting in high forward thrust. Near the end of the roll, it appears the first officer assessed the problem and called for the engines to be shut down, but it was too late. The safety issues identified in this investigation include the critical importance of proper inflation of the landing gear tires on transport category airplanes, and Mr. Swaim will have a detailed presentation on tire issues. The action by the captain to execute a high-speed RTO is also a critical issue. Historically, many rejected takeoff runway excursions have occurred following tire failures and were not warranted. The report examines the possible reasons for the captain making this action, including experience, training, and crew resource management. And Dr. Wilson will have more details in her presentation. The operation of the thrust reverse system following damage to the wiring in the gear well led to the airplane operating opposite to the pilot's command and adding a large amount of speed and energy to the runway excursion. Although similar events have occurred on Lear 60 airplanes in the past, inadequate system safety analyses following a 2001 landing accident were not sufficient to prevent the situation in an RTO case. Additional safety findings in this accident include the FAA procedures for certification of changed aeronautical products and criteria for aircraft tire testing and certification. Parties to the investigation included the Federal Aviation Administration, Global Exec Aviation, Learjet, Goodyear Tire and Rubber, and the Columbia Metropolitan Airport. Additionally, the Transportation Safety Board of Canada assigned an accredited representative and technical advisors as state of manufacture of the Pratt & Whitney Canada engines. I would like to recognize the member on scene, Chairman Hersman, and all the board staff that participated in the investigation. That concludes my opening presentation. Do you have any questions?
Please proceed with the next presentation.
Next presentation is Bob Swaim on tires and maintenance.
Thank you. I will cover tire findings that led to 6 of the staff's proposed safety recommendations. Please note that the tires in this airplane only had about 30 flight hours and 20 takeoff landing cycles. The first anomaly during the takeoff was that the right outboard tire burst as the airplane was passing about 137 knots. Every several seconds, another tire would burst until all 4 were gone and the crew had no brakes. Each of the bursting tires would have been very loud, and as an FAA advisory circular states, heavy pieces of tire material were being thrown at very high velocities. The right inboard tire was second to fail immediately before the CVR and performance studies show that the first officer said, "What was that?" Fragments hit the airplane at speeds high enough to create damage, and the airplane would have undergone the physical motions later described by the passengers. Glass from the right and left landing lights was found on the runway, and a later presentation will show the effects of the damage to a switch that had been near the lights and part of controlling the thrust reverser system. The fifth tire fragment on the runway already had hydraulic fluid on it, so even if the remaining 3 tires, were intact after the first failed, the crew had already lost at least a quarter of the rubber to brake with and potentially had lost the hydraulic system. So the crew lost braking capability early in the sequence. The Goodyear Flight Eagle 178 K43-1 tires had a 14-ply rating and would have been about the height of a small car tire, about half as wide, and inflated to twice the pressure of that used in a large truck. The set of 4 was designed to carry a 23,500-pound load at up to 210 miles per hour. To be able to do this, the pressure in each tire would have been about 219 psi. The left photo shows how thick the tread and sidewalls needed to be, and much of this thickness is nylon fiber to give the tire strength. Despite this thickness, the FAA permits aircraft tires to lose as much as 5% pressure per day, which is about what a car tire can lose in a month. The investigation found that the actual rate of pressure loss for this model of tire was actually closer to 2%, and I will come back to checking tire pressures in a minute. Even this thick construction flexes in operation, and flexing rubber creates heat within it. Rubber is an excellent insulator, and the temperature of the thick sidewalls can increase until the nylon fibers which provide strength actually melt. We found evidence of such melt damage in the second and third fragments off the tire, and the loss of strength caused the first tire to burst. Low pressure increases the flexing of the sidewalls. That increases how fast the tires can heat and fail. In our case, we found rub marks where the inner liner of the tire had folded on itself. This was a physical indication that the tires had been operating at a low pressure. As mentioned, 219 psi would have been the full inflation pressure. The Learjet tires were found to lose about 2% per day, and at that rate, from a full 219 psi, without proper maintenance, the tires would need to be replaced after about 8 days when the pressures fell to less than 185 psi. Because the construction of jet tires is so stiff, an underinflated tire cannot normally be seen. By the time an aircraft tire looks soft or one wingtip is lower than the other, both that tire and its axle mate have been so severely damaged they must both be replaced. After 22 days, the pressures would have been about 140 psi, which was the amount of inner liner damage. The Global Exec Director of Maintenance was asked for the last time the tire pressures were checked, and he estimated that it had been about 3 weeks before the accident. So the physical evidence and the interview came to about the same estimated tire pressures for the day of the accident. Separately, we learned that other operators also lack appreciation for how often high-pressure tires need to be checked, or for how easy it is to damage these tires simply by operating at low inflation. The Director of Maintenance related that he used the maintenance schedule shown in the Learjet maintenance manual. What we found was that Learjet was not unusual in how the maintenance manual was set up, in that it did not prescribe when to check tire pressures in the section that relates to service intervals. Learjet has now changed their maintenance manuals. Staff is proposing safety recommendations about tire maintenance for others. Checking tire pressures is technically simple with a handheld gauge as shown here. In response to initial findings in this investigation, the FAA issued an AD for the Model 60 to require that tire pressures be checked in the 96 calendar hours before a flight. These tires are filled with nitrogen, and only an aircraft mechanic is authorized to bring low pressures back up. But investigators asked the FAA if pilots could check the pressures. The FAA responded that once trained, a pilot flying an airplane as a Part 91 general aviation flight could check the tire pressures. But if the same pilot were to fly the same airplane in Part 135 operation, the pilot would not be allowed to check the tire pressures. Even then, checking the tire pressures requires going under the wing, as can be seen here, and that can be a challenge in wet weather or dark. Tire pressure monitoring systems are certainly not new or expensive technology. They are required on all new cars. Some aircraft TPMS have tire heat sensors, which could have been a second means in which TPMS may have prevented this accident. Staff is proposing safety recommendations about pilots checking tire pressures and TPMS. Although the tire aspect of this investigation has really been about maintenance and not checking the pressure often enough, the investigation found reasons for a thorough review of the regulatory requirements that pertain to tires largely since 1979. Rulemaking shows that some of the real-world issues are not tested for because a 150% overload test is assumed to cover them. Some of the example conditions include tests that include camber, which can be the angle created by contacting the ground in a roll attitude, or with deflated tires, or with deflated landing gear struts. Using a computerized pressure plate at Goodyear Laboratories that did not exist in 1979, tests during this investigation documented an increase in sidewall loads from camber, especially at less than full inflation. All tests are conducted with new tires, rather than with the maximum wear that would be allowed for the last use of the tire. As an analogy, brake testing for many years has started with minimum permitted brake pad thickness. All tire tests begin at full rated inflation pressure, rather than at the minimum pressures the airplanes are allowed to operate at. The Goodyear Aircraft Tire Care and Maintenance Handbook shows that tires may fail in as little as 7 dynamometer takeoff and landing cycles if kept underinflated by only the permissible 10%, which is a much more stringent test than most operations. Again, staff has proposed safety recommendation action. Ready for questions? Thank you very much.
Member Sumwalt.
Thank you, Madam Chairman. This accident was the perfect storm. And I say that because accidents are rarely the result of just one single event. And this accident is a very unfortunate example of just that. We had an aircraft charter company that did not properly maintain the aircraft with something as basic as checking the aircraft tire pressure. That led to the tires overheating and failing during takeoff. The captain was startled by the rumbling and the shuddering and the swerving associated with the tire failure, and rejected the takeoff after V1 speed, which is a practice that training and procedures discourage unless aircraft control is seriously in doubt. When the tire ruptured, as Mr. English said, tire debris struck and disabled a micro switch on the landing gear strut, which made the aircraft basically think it was in the air. And since the aircraft thought it was in the air, the thrust reversers automatically stowed, but the aircraft was not in the air, it was on the ground. And the design of this Lear 60, unlike any other aircraft that I flew, any other transport aircraft that I flew, because the thrust reversers had automatically stowed, the engines applied high power forward thrust even though the pilot was calling for reverse thrust. And I feel, and Mr. English, I'd be curious to hear your thoughts on this, I feel that if any of these events were not present, we wouldn't be here today discussing the accident. Do you agree with that?
Sir, there might be some speculation to that, but it is true we don't have any, to go back to your comments about the V1 speed and rejected takeoff at V1 speed, we have no evidence against the airplane's ability to fly, so that is correct. Clearly, as Mr. Swaim has shown, the tires were operated at pressures far below normal and allowable, and that's the direct proximate cause of the tire failure. And the situation you described with the thrust reversers clearly added a great deal of speed and energy to the equation, to the event. While we can't say categorically whether or not without that situation the airplane would have stopped in the pavement or the RSA, obviously a great deal of forward thrust and energy was added to the severity of the outcome.
Thank you. You mentioned the RSA. Did this airport have the required runway safety area?
Yes, it did.
Thank you. as it relates to tires. We like, in the aviation business, we like redundancy. We don't like to have one single failure that can cause catastrophic loss of the aircraft or loss of life. But in this case, Mr. Swaim, it appears to me that this aircraft does have the potential for a single point failure, in that if one main tire fails, they all are likely going to fail. Is that true?
Not directly. We found a number of cases where Learjets had multiple tire failures, but on the opposite side, we don't know what the inflation pressures for those tires were, and that's pretty critical. And so I can't say just yes or no.
Okay. So you think the reason that all four of these failed wasn't necessarily because the adjacent tire failed. You think that they all failed because of the underinflation issue?
It's one of those gray areas is the real answer. We can't say directly because they were so badly underinflated.
If you had a normally inflated tire on the Lear 60, if, say, the right outboard failed, what degree of likelihood is it that the right inboard would fail for properly inflated tires?
We do know that you will overload the design criteria requirement for that tire, but we also know the tires have a margin in their own. That was the 150% overspeed test I mentioned. And whether that overload will reach that 150% is the gray area I'm talking about. I'm trying not to get into percentages and pressures and all that kind of thing. But once you lose one tire, that's why we have a recommendation to go back and relook at the regulation and how firm it is, how substantiated it is.
Thank you. You mentioned that you found hydraulic debris on some of the tire fragments, so what does that indicate to you?
Well, the hydraulic fluid on tire fragment number 5 and then a few later clearly comes from one of the hydraulic components in the landing gear well. We have both fused and unfused. The fused components, such as for the brakes, would stop flowing with a massive leak. But we do have 2 lines, a pressure and a return, that are not fused, and without those, you would lose the hydraulics of the airplane.
Okay, thank you, and thank you. I have no further questions.
Vice Chairman Hart.
Thank you. Mr. Swaim, I had one question. You said talked about the tire losing 2% a day, and that if without maintenance, it would need replacement after only 8 days. But I think you said replacement of the tire and something else, and I didn't get what the something else was.
If the airplane's operated with 185 psi or less, that would be the number that would apply for this airplane, this tire. If the airplane's operated at that point, the tire and the axle mate would both be assumed to be damaged to the point of requiring replacement.
Okay, that's what I didn't understand. The tire and the what?
The axle mate, both tires on that side of the airplane.
Oh, axle mate. Okay, so you didn't mean the axle itself. You meant the accompanying tire on that same.
Correct.
On that. Okay. Okay. Thank you very much.
How long had it been since the tire pressure had been checked on the accident airplane?
Physically and from the interview, we believe 3 weeks.
And if the tires were properly inflated at the beginning of the 3-week period before the accident, and they had a daily loss rate of about 2%, they would have been underinflated by how much on the day of the accident?
We believe they would have been at about 139 point something psi.
About 36% underinflation?
Correct.
Is the 36% underinflation consistent with our post-accident testing that were performed on the tires?
I'm sorry, I don't
Did we
understand.
see results that were consistent with this type of underinflation in post-accident testing?
Well, it wasn't testing, it was examination. Yes, we found the inner liner of the tire had folded and chafed to that point.
One of the things that you mentioned was that after about 8 days, without checking the tire pressure or adding air, that they would need to be replaced. Do you think that most operators understand that?
We found they do not. And we did find some operators that, through some surveys, let their airplanes operate at a bit less than that repeatedly. There is a safety factor, fortunately, in the design of the tire to accommodate for that.
I noticed that in your factual, there's a figure 72, and it talked about a tire pressure survey for light jets. And I don't see any of the jets that were listed on the data that was recorded by a fixed base operator being less than a 5-day check. It goes out to 25 was the longest interval days since last checked, and 5 is the shortest interval. Do we think that 5 days is appropriate interval for the tires to be checked? Certainly we know 25 is not, and we know 14 is not, and we know 13 is not, and we know that 9 is not, but what about 5? Is that right?
It's not a question of the number of days. It's the question of, does the tire have the minimum required pressure when you take off?
Okay, so
it's not a question of calendar, it's a question of pressure.
Right, but you've made it very clear that pilots and even trained mechanics cannot tell by looking at a tire whether it's properly inflated. And so we know that people need guidance, they need checklists, they need standards, they need intervals, they need to know how often they're supposed to perform something. And so if we're looking at, some 20 aircraft at an FBO and how often they're checked, it doesn't look like anyone has a real good handle on how often they need to check the air in the tires.
Could we have backup slide number 12, please? While she's looking for that, Chairman Hersman, what we found is, the reason I'm asking for the backup slide to be brought up is it's an example of the pressure survey that we did. And it's an example of what is actually a pretty good operator, a pretty good fixed base operator, who goes out and, without being required to by the maintenance manuals, has his airplanes in his hangar checked once a week. And so that's where this data came from. And like I say, he was a pretty conscientious operator. There we go. And so you can see different airplane models, and I just simply asked them to write down what they came up with each time they went out and checked these airplanes. And that's how we got this operator's data. And like I say, he was pretty conscientious, but we know there are folks who go well over this.
Okay. Do you think that operators have any sense that after 8 days, without checking or adding air, that they need to replace their tires, that they'd be so underinflated that they'd need to replace them?
No. It is a requirement in the maintenance manual that when you're at a certain percentage low, and the maintenance manuals give a hard PSI number for each model, they say at this point replace the tires, but it's not given in terms of days.
Okay. And to follow up on a question that Member Sumwalt asked, he asked you about the expectation if a right outboard tire failed, would we necessarily expect the right inboard tire, the axle mate, so to speak, to fail? And I note in the in your factual, you talk about the static calculations for that Learjet performed on the tire loads. And they're assuming 100% inflation and on all the other tires, but a loss of pressure in tire number 4. And it looked like the right, when the right outboard tire had 0 pressure, the right inboard tire was loaded to 213%. And I appreciate that you said that tires are tested in excess of the 1.07 factor that they're required to be to 1.5. But would that be 150%?
Yep, that would be 150%, and we are concerned about this. The FAA is aware of it, and we know they are re-examining, and it's also the basis of our safety recommendation in front of you.
Okay, great. I have some more questions, but I'll yield to Member Summerall.
Thank you. I think one take-home point for me coming out of this accident is that I never, as a pilot, never really appreciated the importance of tire pressure. Now, granted, most of my experience was in a 121 environment where a mechanic was looking after my airplanes, but after I left the airline, I went and managed a small Part 91 flight department, and I, with my piloting background, did not take the tire pressure issue seriously, and so I've learned something pretty useful here. Let me ask you this. The King Airs that we were operating, the manual said that the tires should be at about 80 to 90 psi, whereas this Lear 60, they're 220 psi. So my question to you is the Lear 60 with its 220 tire pressure, 220 psi tire pressure, is that more significant in terms of maintaining proper inflation than, say, another aircraft like the ones that I was managing where it's less than 100 psi? Is it still as critical?
Either airplane needs its tires to stop you and to take off safely, both airplanes. The difference is your lower pressure tire has a lower difference in pressure between the inside of the tire and the ambient air around us. And that differential pressure influences the leakage rate. So your 80 psi King Air is going to leak at a slower rate than your 220 psi Learjet tire.
Thank you. And I will speak to a group next month out in Tucson, and I think that this is a take-home point that I will want to make for the corporate operators, is that checking tire pressure is a very important issue, and again, it's not something that I fully appreciated until now. Thank you.
Vice Chairman.
Is the 2% a day, is that a number that's typical for airplane tires in this class of airplane, or is that an FAA maximum limit, or is that what these tires did, or what does the 2% a day represent?
The 2% per day was fairly typical for this model of tire. The 5% is what the technical standard order, the FAA's document, says tires can have as a maximum. So 5% would be the maximum by the FAA. 2% was about what we were finding on the Learjets. We found them as low as 1.1% per day. Some of your lower pressure tires on your single engine Cessnas, for example, they're down in the low leakage rates almost like a car.
Okay, so that's what I was trying to understand, was that I didn't want the discussion to be too generic to all tires if the 2% was specific to this tire. Is that
2% for this tire, but this tire is fairly typical for a high pressure tire. That's a very key point. These business jets, the smaller jets with the high loaded tires where you see such a thick wall of the tire, that thick wall is there for a reason. It needs that strength because those tires are so heavily loaded. And so they need that 200 and plus PSI. Dassault, the Falcon has similar tires. Embraer has a couple of airplanes. As a matter of fact, one of these tires is used on an Embraer airplane.
Do we have any comparison? I didn't notice it in the report, but do we have any comparison with, say, Navy jets that land on carriers that typically have very high pressures too? Do we have any comparison of how the tire, the daily leak rate typically or anything like that? Did we look into any of that?
We have nothing in the report, but they are similar. These originally back in an earlier iteration, a thinner wall tire that was not as highly stressed, they were adapted from a fighter use.
Okay, thank you. That's very helpful.
Mr. Swaim, when the tires were approved for the aircraft, what were the assumptions that were made as far as safety factor that might have been built in? Did they assume any underinflation? Did they assume any wear? Did they assume failures, tire failures, adjacent tire failures. Can you tell me what kind of assumptions were made when this tire was approved in the certification process as far as the weight of the aircraft? Let's just talk about what safety margins might have been built in.
If we could have backup slide number 1. These are the main requirements on the tire according to the FAA's regulation and the technical standard order. One tire in a dual installation, like on the Learjet, has to be able to support 107% of the axle weight. In other words, support that side of the airplane plus some. They do these taxi tests, they do these takeoff tests, and they're very strenuous. The airplane's loaded to full rated gross weight. The tire, is loaded to the rating of the tire, which is beyond the gross weight. Misstated that at first. And then they're run to this 150% and 120% load. So those are pretty strenuous tests. As far as additional requirements, some of the aircraft manufacturers place them. If they want not 150% load, say test it to 160%, they can do that. Some do, Boeing and Airbus, for example. As far as foreign object damage, low pressure, those are not part of the testing. NHTSA picked up similar tests after the Ford Explorer Firestone problems around the year 2000.
And so one tire, as far as the certification regulations go, one tire has to support 107% of the axle weight. The assumption there is that it's fully loaded, not overweight?
Yes.
The aircraft. And this aircraft exceeded the airplane's gross max weight?
By a very, very small margin, which Captain 2 may have the numbers for, but it was very minor.
Several hundred pounds?
It's a guess because we don't have the exact numbers because we couldn't weigh the stuff, but our best guess is just a couple hundred pounds.
And do we think that that affected or contributed to the accident?
You mean as far as the tires?
The weight, the additional weight.
Mr. Swain could certainly answer the effect on the tires, but the airplane I think would be capable of handling that.
Okay.
We're talking less than 1%. So probably not. Percent divided by the 4 tires.
Okay. I think in this investigation we uncovered a lot of information about standard procedures, what was going on, some guidance in manuals that may not have been followed, saying do daily tire pressure checks. In an operation like this, are the pilots trained to do daily pressure checks before the first flight of each day?
The pilots are not required, at least Global Exec. Different operators may have different requirements. Captain 2, anything?
There was one Learjet operator that the pilots were trained. They carried a tire pressure gauge, but generally the tires are not checked by the pilots.
And if these operators, many of them are flying to charter operations, they don't even, maybe the pilots don't even know where they're going to be the next day. They may be getting told to dispatch somewhere to pick up a customer. Is there an assumption that there's always going to be someone there, no matter where they are, what time they land, to check the tires for them?
No, I wouldn't think so, because some of the outstations wouldn't have that kind of support. But if the tires are checked on a regular basis, they should be okay. That's what I think we're recommending, is that we set up a good schedule for.
Right. So the guidance that's in the manual that says daily pressure check before each flight really was not followed, and it wasn't practical. Pilots weren't trained. They didn't have the equipment. They weren't doing the checks. And certainly in this type of operation, in this industry, it wasn't happening. Did the FAA understand that it wasn't happening?
We would have to ask the FAA, ma'am.
Does the FAA have information about tire failures?
Yeah, they have the SDR reports. They have access to the manufacturer's records, customer service records. They have the damage reports to the airplanes. Again, when these tires go off, it will definitely be a very major event in a small airplane to have one of these tires go off, to burst. One of the FAACs calls it a potentially violent event. And so in that, I know folks don't like to use that word, but it is a 220 psi object that's coming apart explosively. And so we are damaging the airplane. And so the FAA does have records of those.
And what are the records? You're saying they're SDRs?
Yes, ma'am.
And I know, Mr. DeLisi, we've talked in the past about SDRs. What percentage of reports actually get filed? Do we have an estimate on that?
I think years ago we came up with an estimate that about 10% of service difficulties were actually reported.
Okay, so let's just talk about data, because we have a lot of interest in data and using data to tell us where our problems are, and using the data to identify what safety steps need to be taken and how remediation should be done. And I think a lot of people at the FAA believe that data is the way of the future, and forensic accident investigation is a little bit passé. Tell me what kind of data that the FAA had about tire failures that might have helped them to identify this widespread problem with detecting underinflation. Did they have data? Was the data there?
Again, the source of data for an individual tire failing would have to be a service difficulty report. That's non-routine maintenance. Operators are required to fill out an SDR report every time they do non-routine maintenance. They couldn't look to us. A single tire failure is not an accident or a reportable incident, so we don't archive any sort of record of the frequency with those events happen.
Let's say we have a Lear that fails 4 tires and a rejected takeoff but stays on the runway. Would we know about that?
That would not even be a reportable event.
Okay, so who's the keeper of this data?
Again, the SDR database would be the place that non-routine maintenance items should be logged in.
And when we asked the FAA to look at their SDR database after this accident, did we have any sense that there was a problem?
What was missing is that nobody had brought together the thought of looking at these different tire events. Nobody had, basically what it came down to was what one of the manufacturers said, we're no different than anybody else, but they didn't have the other manufacturers' data to compare to. And the FAA had the SDR records, but they hadn't had a cause to go out and start comparing different manufacturers' data. On top of that, as you mentioned, I have a number of multiple tire loss events listed in my factual. But what the FAA had quit collecting years ago that would make sense of that is in annual inspections of airplanes, they used to collect how many hours per year the airplane has flown. They don't even collect that basic information anymore.
So the operators don't have comparative information. They think I'm just like everyone else, but they don't know if they're like everyone else. Does FAA have a baseline to be able to determine if there are any spikes in any particular operator's tire performance?
Not that we know of. Perhaps a methodology where the principal maintenance inspectors were tracking tire usage or replacement might be a valuable way to see what sort of trend an operator is having, but there's no other data source.
Okay. I thank my colleagues for letting me go over. Remember somewhat?
Thank you. I just have one follow-up question in response to a question posed by the chairman, and that is, I want to make sure I understand this right. Is it an expectation of the flight crews to check the tire pressure?
I'm sorry, what do you mean, an expectation by the flight crews? That they do it or that it has been done?
That they do it.
In the current AFMs, it does not tell the flight crews to do it. It just, in the maintenance manual, it says you should have it done as an operator. Now, how the operator implements that is up to the operator.
Right, so the pilots are not expected to actually physically check the tire pressure. I'm looking at the QRH normal procedures for the Lear 60, and it says right main wheels, right and left main wheels, tires and brakes checked. It doesn't say check the pressure, and it's interpreted by the pilots. That means a general condition of the making sure there's no cord, making sure that there's no chips. And does anywhere in the POH, Pilot's Operating Handbook, does it even say what the tire pressure should be for this aircraft?
No.
So this is a maintenance function. It's not expected of the pilots to check the tire pressure. Do you agree with that, Captain Two?
I certainly would.
Okay.
They're only supposed to check the condition.
Thank you.
I think we're ready for the next presentation.
Next on the agenda, Dr. Catherine Wilson with the crew actions.
Good morning. As previously discussed, the captain performed a high-speed rejected takeoff, but wavered during its execution by first reducing engine power and then subsequently increasing power before fully committing to the RTO. I will discuss factors surrounding the captain's execution of the rejected takeoff, including pilot experience, training, and crew resource management. The captain had accumulated about 3,140 hours total flight time. She was type rated in the Learjet 60 about 11 months before the accident and accumulated only 35 hours in the airplane, including 8 as pilot in command. During the same period, the captain also became type rated in the Cessna Citation 650 and flew at about 118 hours. Staff is concerned that the captain was flying 2 different type airplanes and acting as pilot in command when she had limited experience in each airplane. The captain lacked confidence during the accident sequence, as is evidence of her wavering during the RTO. Regulations for Part 135 on-demand operations do not require pilots to gain a minimum level of initial operating experience before serving as pilot in command. Gaining the necessary knowledge and skills within a specified period of time from when the type rating is received increases a pilot's confidence in handling the new airplane and facilitates timely and appropriate responses to an abnormal situation. Staff has proposed recommendations in this area. The flight crew received Learjet 60 training from Flight Safety International. Training guidance specified that a rejected takeoff is acceptable for any anomaly occurring before the airplane reaches 80 knots. Between 80 knots and V1 airspeed, a rejected takeoff would only be acceptable for major anomalies such as a catastrophic failure or engine fire. V1 is generally the maximum speed by which a rejected takeoff must be initiated to assure that a safe stop can be completed within the remaining runway. Guidance specified that above V1, the takeoff would be continued due to the high risk of a runway overrun unless the airplane's ability to fly was in serious doubt. In addition, pilots were instructed to remove his or her hand from the throttles at V1. Simulator training included practicing rejected takeoffs due primarily to engine failures at or around V1 speed or an inadvertent deployment of thrust reversers. Pilots did not receive training on tire failures. The captain verbalized the rejected takeoff procedure during the pre-takeoff briefing. The captain incorrectly stated that the takeoff may be rejected for major anomalies occurring between V1 and V2 speeds, which was contrary to training and standard operating procedures. Staff considered whether the captain was unfamiliar with the concept of V1 as it related to the go, no-go decision. However, there was no evidence to support this. And because V2 occurs after the airplane's rotation speed, it is unlikely that the captain would have considered V2 to be part of the rejected takeoff criteria. Her statement was most likely a slip of the tongue. And although the captain rejected the takeoff after V1, as she stated in her briefing, evidence indicates this action was likely associated with being startled due to the sudden onset of and ambiguous cues associated with the event. For example, the pilot's statements reflected uncertainty over what they were experiencing, and there was no evidence to suggest the airplane was uncontrollable. The FAA's takeoff safety training aid acknowledges that tire failures may be difficult to identify from the flight deck. The guidance emphasizes that pilots must be cautious not to inappropriately conclude that another problem exists and mistakenly reject the takeoff. Furthermore, the chances of an overrun increase due to the loss of braking force from one or more tires. A special investigation conducted by the NTSB in 1990 on the causes and outcomes of high-speed rejected takeoffs revealed that tire failures led to more high-speed RTOs than did engine-related anomalies. However, training for this type of failure is not typical in the industry, and staff has proposed recommendations in this area. When used effectively, crew resource management enhances crew performance in the cockpit, and it is the captain's responsibility to assume a leadership role and set the tone in the cockpit. Although not required under Part 135 regulations, the accident pilots practice CRM skills during simulator training, but interviews with instructors did not reveal specifically what skills were trained or evaluated. The CRM skills exhibited by the flight crew during the accident flight were inconsistent with the skills needed for effective communication and the coordination of a professional flight crew. For example, during the taxi, there were several instances in which the captain or the first officer read back incorrect information, and the mistake went uncorrected by the other crew member. Additionally, after the captain stated the incorrect RTO criteria, the first officer did not directly question her error. And finally, the captain's casual tone and lack of leadership and the flight crew's inattention to details foreshadowed elements of the captain's execution of and wavering during the RTO after V1. The NTSB has longstanding concerns about the need for CRM training in Part 135 on-demand operations, and this issue is on the NTSB's list of most wanted transportation safety improvements. The NTSB previously recommended that CRM training be required for Part 135 operations. Although the recommendation is currently categorized as open acceptable response, the FAA has yet to complete action in this area. Thank you.
Thank you, Dr. Wilson. Member Sumwalt.
Thank you. Dr. Wilson, you made a statement that I'm not sure I agree with. As a pilot, you indicated that the captain's wavering was because of lack of confidence. Is that basically what you said?
Well, we think as a leader, if she was going to commit to the RTO, that she would have fully committed to the RTO. We found that after she first rejected and the first officer told her to continue the takeoff, she increased power, and then for whatever reason, we don't know whether she didn't feel that the airplane was speeding up or she felt that it was too late and she needed to fully commit. That was when she fully committed to the RTO. Okay, thanks. And what I do think you initially said was because, and I think the report says this too, something along these lines, that due to a lack of confidence, she wavered. But as someone who's been there myself in a high-speed reject, could it be not so much a lack of confidence, but because of the startle factor associated with the tire failure? Definitely the startle factor played a role in this, but we also feel that her lack of experience in the airplane, we felt that she wasn't very confident in her ability to handle the airplane. She turned to the first officer a lot of times during the taxi, asking for his guidance on sounds that she was hearing, and so we just felt that there was a pattern of her not being comfortable as pilot in command. Yes, and I do agree with what you said early on, and let me just take a peek at that. She was type rated on the aircraft 11 months prior to the accident. She had 35 hours in the airplane, and 8 of which were PIC. And then she got type rated on a Citation 650, which I think is a Citation 3, I guess. And the fact is that I cannot imagine going out 11 months after I was trained with only 8 hours PIC after having flown other airplanes. And flying an airplane in an airline environment, in a Part 121 environment, you're going to go out as soon as you get type rated and get 25 hours of initial operating experience, and then you've got to get in 120 hours or 100 hours, I guess, whatever the time is, within 120 days to consolidate that learning. So I do agree that there's a large gap
between her initial training and this flight, and that's not desirable. So I do agree with you on that. The reason I wanted to question the confidence issue versus the startle factor is that I will get into this in the next round of questioning, is that training is key. These things are going to startle people. I know that from experience, and so we have to train accordingly so that the first time they see this isn't at midnight on an unfamiliar airport. I'll come back to that later, but let me ask a couple more questions, and then I want to come back on the next round. Could this aircraft have stopped on the runway if the uncommanded forward thrust had not occurred?
Member Sumwalt, there is a great deal of speculation involved in answering that question. We are somewhat hampered by the fact the airplane did not have an FDR, so some of our data is got a little bit of, excuse me, some error to it, and the fact that there is no test data for the stopping capability of an airplane with compromised rubber. In other words, no tires on there. So some of these estimates are just that, estimates at best. Learjet did provide us with some estimated numbers on the stopping capability of the airplane, depending on the particular scenario. In this case, if the reversers worked properly or stowed and went to idle, as in our recommendation package, we really can't say for certain where the airplane would have stopped. But as mentioned earlier, there definitely would have been much less forward energy acting. The engines were developing upwards of 85% or more, possibly forward thrust at the time of the event because of the stowage scenario. And the tires are a great part of the stopping capability. So while I don't want to commit to saying where the airplane would have stopped, clearly the situation was very dangerous, and the engine situation contributed to that.
Thank you for that. So if we were to sum that up, the fact that the airplane went into forward thrust as opposed to reverse thrust certainly exacerbated the situation. Do you agree with that?
Absolutely.
We know that a takeoff should not be rejected above V1 unless aircraft control is seriously in doubt. And do we have any indications that the aircraft would have been uncontrollable had the takeoff been continued?
We have no evidence against the airplane's ability to fly.
So what you're saying there is that since they were after V1, even though they were shuddering and rattling and banging, probably the safest course of action would have been to continue the takeoff, come back around, land on the first part of the runway instead of trying to stop on the latter part of the runway where you've got 8,600 feet available runway versus whatever was left by the time this takeoff was rejected. Is that basically correct?
Yes, sir. The crew actually did brief, if they had certain problems after takeoff, they could return to Columbia, or they could divert over to Charleston, which has an even longer runway. To answer the question, if they did take off, again, there is quite a bit of speculation there. As I said, we don't have evidence against the airplane's ability to fly. Now, what the captain perceived, obviously, is in Dr. Wilson's area, but historically, this type of situation, landing, even if they did have a partial gear problem, historically, these are not significant events. Airplanes might go off the runway or something, but they're typically low speed and don't cause serious damage.
Thank you very much.
Vice Chairman Hart.
I'd also like to explore the, you said we don't have evidence that the airplane was uncontrollable, but let's look at what the captain was thinking at the time, given what the captain knew or didn't know. She knew there was a loud noise, and then there was a startle associated with that. Things are vibrating. I think there was a loss of directional control momentarily associated with the tire. I don't want to misstate, but what was the directional control situation?
I think your distinction is very good, Vice Chairman Hart. There is a skid or swerve mark evident on the runway for a brief period of time, but it is important to distinguish between what evidence we have in hindsight looking at the aircraft and what the pilot might have perceived, and I would defer any perception questions to Dr. Wilson.
And then I would add to that her lack of training. I've never seen sim training with a tire failure either, so I'm not familiar. I don't know that that ever happens. I think that's kind of consistent with what you said in the report, but I'm thinking, so she has never been through this before. This is a complete new situation for her in the sense that, you know, loud noise, vibration, directional difficulties, et cetera, et cetera. So I guess I'd like to hear that analysis more in terms of what she thought at the time rather than what we now know in hindsight.
Well, we definitely know that the noise was very loud, I'm sure very startling, ambiguous. Again, both crew members said that they didn't know what they were experiencing. And again, she did have that swerve. We did have a picture of the swerve on the runway. She swerved a little bit to the right, but quickly regained control, and the airplane actually paralleled the center line all the way down the runway. So the directional control issue, we think, was very momentary. And, you know, we'll never know really what she was thinking, but that was why we want to encourage training for this. This is something that is not trained, but from the research that we've seen, these events occur at the same rate as high-speed rejected takeoffs due to engine anomalies, and sometimes they occur even more frequently. So, and because the cues are so ambiguous, we really feel that training for it is just as important as engine failures at V1.
Do we know if the first officer had ever had either an actual experience of tire failure or training regarding tire failure?
We do not know if he ever experienced a tire failure. We do not know if he experienced it in training, and based on interviews with instructors, they said typically that is not an event that they include in training. While they're allowed to include it, it's just something that is not typically done.
Okay, thank you.
Antoine, I'm going to be looking for that video shortly, just a heads up. And Mr. Marcus, also I'll be asking you about the status of some recommendations that we issued in the 1990 report. Had the captain had training on rejected takeoffs and V1 cuts?
Yes.
And were those mostly engine failures? Or what other scenarios would she have seen?
She received engine failures and also an inadvertent deployment of thrust reversers on takeoff.
And what is the response that is trained for inadvertent deployment of thrust reversers on takeoff?
You just put the power levers down to the stow them, basically, because you don't want the reverse thrust coming up. Now, I would comment, just to add something, the captain did get a inadvertent thrust reverser during training, we noticed, but in rereading the interviews, I noticed that one instructor particularly mentioned that that was usually done at the lower speeds. He didn't get it at a higher speed, which is significant.
Okay. And the information that would have been presented to the pilots to recognize that they were having a malfunction with what they expected for the thrust reverser, would they have had any warnings, any bells, any lights? Would they have had any movement of the handles to signal to them that they weren't getting what they were commanding?
Yes, I've got my presentation covered that pretty good.
All right. Dr. Wilson, did either of the pilots in the cockpit identify the failure? Did they identify the problem that they were having? Did they state that there was a tire failure? Did they appear to understand what was going on?
They did not. The first officer stated to the captain, "What was that?" And she said, "I don't know."
So given that you don't know what the failure is, what do you do in response? Is there a consistent trained reaction when you have some sort of anomaly? What are they supposed to do?
Well, in those situations, the amount of time that they have to analyze and make the decision is a split-second decision, and that's why there's training for V1 cuts and standard operating procedures that after V1 you're to continue to take off, and also removing the pilot's hand from the throttles to avoid that gut reaction to pull the throttles back when something like this does occur.
And they get training in the simulator. They also have other types of training. I think in the report we talk about a Boeing video that this operator provided to its crew members. Do we know if either of these crew members watched the video?
We do not know.
Antoine, if you could pull up the tape and roll tape. I'm going to show about 1 minute of that video, which I watched. Do you know what year this was produced?
I believe it was 1992.
Remember, V1 marks the end of the go, no-go decision time. If you have not applied the brakes by the time you reach V1, you have made the go decision.
Although historically our training has centered on engine failures as the primary reason to reject, the statistics show that wheel and tire problems have caused just about as many accidents and incidents as have engine events. Other reasons that rejects occurred were for configuration, indication or light, crew coordination problems, bird strikes, or ATC. Undetermined causes make up the rest. What's important to note here is that the majority of past RTO accidents were not engine failure events. Full takeoff power from all engines was available.
Thank you, Antoine. Mr. Marcus, I noticed that that same chart that I was just up on the screen is actually included in our 1990 Special Investigation Report. And one of the recommendations that we issued in our Special Investigation Report had to do with training for RTOs and tire failures. We specifically, in A9041, we asked the FAA to require I'm sorry, and it was 90-40. No, my apologies. Sorry, I'm trying to read this rec letter here. It is 90-43. Required that simulator training for flight crews of 14 CFR 121 operators present, to the extent possible, the cues and cockpit warnings of occurrences other than engine failures that have frequently resulted in high-speed rejected takeoffs. And Member Sunwalt, I know you were flying in a 121 operation during those years. Did you ever have simulator training for anything other than a engine failure? Would you have seen a tire failure?
Yes, we did have training for RTOs for things other than engine failures, but I can't say whether or not tire failure was part of that.
And Mr. Swaim, I remember when we met that you talked about how violent potentially this experience might feel. And I read some of the information that was contained in the docket about some of the testing that had been done on tires. And because it was so, the shedding of the material was so significant, they had diamond-plated walls in the test facility that had dents in them. Can you articulate to me what it might have felt like as pieces of the tire might have been hitting the wing or the aircraft? I think you represent it to me like a bowling ball.
Well, it's Dr. Wilson's area for what it would have felt like. We do have the statements from the two surviving passengers. One said that it felt like a wingtip fell to the ground. The other talked about feeling like they'd lost control. Those being from passengers in the back. We know it would have been very noisy because we covered the CVR with white noise. 1 ounce of rubber coming off at those speeds would have the force of a 16-pound bowling ball. That's what I referred to. That comes out of some calculations from, I believe, the Michelin Tire Care Handbook. So we have intermittent marks in the runway from the carcass going around on the wheel. Slamming the landing gear strut up and down. We have the initial deviation in their track, the swerve, but we can't tell what they physically had because we don't have any FDR data.
Okay, and my time's up, so I'll finish my round when I come back. Member Sunwalt.
Our draft report talks about the takeoff safety training aid coming out in 1994. The reality is that was the advisory circular that referenced the takeoff safety training aid. The takeoff safety training aid is this document here. This document came out in 1992. And I'm going to get to that in just a second. High-speed RTOs are inherently risky. The takeoff safety training aid states that 58% of RTO accidents and incidents reviewed by Boeing were above V1, were rejected above V1. And in most cases, the aircraft was flyable. So that tells us that the reject didn't need to take place. The airplane was in an airworthy condition. Again, as you pointed out, Mr. English, that may not be the same as the flight crew's perception, but after the fact, it was determined the aircraft could have flown. US Air 5050 would be an example of that certainly hits close to home for me, since it was the airline I flew for. Takeoff safety training aid says that nearly 1/4, and we saw a graph, 1/4 of RTO-related mishaps were related to wheel and tire failures. And in 1985, a NASA-operated Convair 990 crashed at March Air Force Base following a high-speed reject. The airplane went off the end of the runway, burned up, and that was the end of the airplane. The NASA Accident Investigation Board report stated, and I quote, "Statistics indicate that RTOs in response to tire problems are 4 times more likely to result in an accident or an incident than those in response to engine problems." End of quote. And so as a pilot, I know that tire failures can create an element of surprise and uncertainty. And that's a lot of the problem here, is the element of surprise, the loud noise. You're startled by the noise. You're startled by the shuddering, the rattling of the tire hitting the airplane, and the rattling of now riding on rims on one side of the airplane. The aircraft will likely swerve, as we saw in this case. The tire debris can strike other parts of the aircraft and cause damage. Sometimes the tire debris can come up and disable engines. It can take out hydraulic systems, as we saw in this accident. It can puncture fuel tanks, as we've seen. And if you reject the takeoff, your braking efficiency is severely hampered because the tires that you were planning to use to help you stop with aren't there anymore. And Dr. Wilson, you're a human factors expert, but I don't think you even have to be a human factors expert to recognize that pilots, like all humans, don't do as well with unfamiliar situations as we do with familiar situations. So would you agree that training is key?
Definitely.
Yeah, we need to better prepare pilots to deal with situations such as tire failures, and certainly we need for them to experience and practice properly reacting to tire failures in the simulators, so that, as I said earlier, so that the first time they see it isn't literally in the middle of the night at an unfamiliar airport. Now, this takeoff safety training aid was published in 1992, and it was a lot of work involved. I know the people, some of the people that were involved in putting it together, and it's hundreds of pages. It even contains the NTSB's Special Investigation Report that was done in 1990. It's got an overview for management, a pilot guide to takeoff safety. It's got academic training programs. It's got sample simulator training programs, including simulator exercises, simulator fidelity checks. It's got the part of it was the video that we just saw a piece from. A lot of background information, a lot of information. But there's a saying that those who don't remember the past are condemned to repeat it. This accident in Columbia, South Carolina, occurred 16 years after this takeoff safety training aid was published. The captain would have been about 15 years old when this document came out, and she was not even a licensed pilot at that point. We must ensure that the lessons from prior accidents perpetuate not only in the Part 121 community, but in the 135 community and in the Part 91K community. The SIR, Special Investigation Report, referenced by the chairman, is titled Runway Overruns Following High-Speed Rejected Takeoffs. And in that, the board issued several recommendations to improve the quality of pilot training. These recommendations were closed as acceptable, but I note that these recommendations were to Part 121 carriers. They did not necessarily improve the quality of training for Part 135 pilots or Part 91 pilots. So where I'm going with this, and there is a point to it, staff has proposed 2 recommendations regarding improving training simulator fidelity for tire failures that include realistic sound and motion cueing. First question, and I support these recommendations, but I have 2 questions. The first is, who is the intended audience? We didn't specifically say in the draft rec for Part 121 or 135 or 91K, we left that part blank. Who is the intended audience for these recs?
Well, obviously, this accident ties directly to Part 135 on-demand operations, but we do think that it's just as important for all 135 operators and 121 operators.
Okay, and how is the FAA going to know that when they read our recommendation? Is it sufficiently vague by reading these to find and codify minimum simulator model fidelity requirements for tire failure scenarios? And once these are implemented, require that simulator training for pilots who conduct turbojet operations include opportunities to practice? Is that, I mean, I'm just asking the question, are we confident? And it does say for turbojet operators, so that would seem to incorporate 91K, 135, and Part 121. Are we satisfied with that?
Yes, that was the broad brush we were trying to use there.
Okay, good. Just wanted to make sure that we had thought through that. I'd prefer not to have a situation where we had from the SIR in 1990 where we target a specific group of operators. We basically cured that problem because the 121 operators have incorporated. The FAA has ensured the 121 operators are following those recs. So I don't want to leave anybody out this time. I'm over my time. My second question will have to wait for the second round. Thank you, Madam Chairman.
Vice Chairman. And let me follow up on that because I looked at the rec history on 90-043, and I think one of my concerns was that although we closed the recommendation in an acceptable alternate action, it almost seemed that we were closing 7 recommendations issued as a result of the special investigation report based on the training aid and the AC. I didn't see how they specifically responded to the simulator training for tire failures. Mr. Marcus, did they specifically respond to the recommendation about simulator training and adopt that and incorporate that into Part 121 training?
My reading of the recommendation history is the AC, and also they came out with a bulletin to all of the inspectors to check and make sure that the training programs are up to date. I did not see anything related specifically to simulator training. I believe the assumption was that that would be done in what was in the programs.
And I think that was one of those situations where they were heading in the right direction, but it wasn't accomplished. Captain 2, Dr. Wilson, did you all find that any of the providers for training were providing training for rejected takeoffs or continuing the takeoff in the event of a tire failure?
We didn't find any evidence of that.
So I think part of the challenge is obviously I think we've, in 20 years, we would likely not have closed this type of recommendation, I think, today, had we not seen actually a program for simulator training. I think what we saw is that we did close this recommendation, but I think unfortunately, we're here and it's 2010 and we're learning the exact same lesson that we learned 20 years ago. Our SIR is very clear about the value of training and the startle effect, and the fact that many pilots make the wrong decision even after V1. And so I think that there's an issue here, and I'm going to get back to the concern about data, because I think the data was plentiful and available and clearly providing a direction of what needed to be done, and it wasn't done. I want to follow up in an area that I think my colleagues have talked about, Dr. Wilson, and it's in conclusion number 22. We talk about in conclusion number 22 that one of our concerns about the captain was her limited experience as PIC, and it contributed to her indecision and failure to follow standard operating procedures. I was just curious, do you think that more experience would have resulted in her making a different decision?
Definitely think that it would have, and the one thing that we're recommending is that pilots not only gain, as Member Sumwalt was saying, initial operating experience flying the airplane, which is under a check airman or a qualified individual who's monitoring the new captain performing the duties as pilot in command before they're released to fly on their own. And I think the fact that this captain only had 8 hours of pilot in command in this airplane and was also switched between this airplane and another airplane didn't allow her to really consolidate the knowledge and skills that she needed to act as pilot in command.
There's a difference between having the knowledge and experience to operate as a pilot in command and responding appropriately to this event. And so I think the focus here is that her limited experience as PIC contributed to her indecision and her failure to follow standard operating procedures. And I think that's specifically that V1, post V1 decision. And I recognize that more experience would have been helpful to her as far as her command presence in the cockpit, but we have a lot of examples. Over half of the rejects are past V1. They're not all new pilots. Many of them are very experienced, and on page 80 we talk about an FAA flight test manager who had been part of the certification process for the Learjet product line, recalled having once been involved in a high-speed RTO in a Learjet 55. He stated at the time that he was in the first officer's seat. A Learjet company pilot was in the captain's seat. They were performing a takeoff at gross weight in Orlando, and all 4 main landing gear tires came apart after the airplane was beyond V1. What would you have expected for this FAA flight test manager and a Learjet company pilot in the captain's seat? Did they have enough experience?
I think what we had that was different here was that she wavered on her decision, and we feel that if she had had more confidence, we don't doubt that this event was very ambiguous and startling, and she did react in ways that other pilots have acted on many occasions. But the wavering during the rejected takeoff is also of concern to us. So one, rejecting, we can understand that, but the indecision that she had and not fully committing to her decision also exacerbated the problem.
Well, I think the challenge is in this case, we had 2 pilots who were experienced and they knew what was going on because they saw the tire fragments. And of course in post-accident recollection, they survived and they lived to tell the tale and they had to talk about it. Well, they decided that, well, the reason why we rejected after V1 was because we were concerned about engine ingestion. Okay, fine. But this crew didn't even know what they had. They didn't even know that they had a tire failure. And I think that that the challenge with the indecision, for me, I'm struck. We always are kind of frustrated with pilots when they don't listen to their co-pilot. So her indecision lasted for about what, 1 second?
I think it was actually a couple of seconds, 2.5.
Depending on how you read it, 2 seconds or so. Yeah.
I mean, there's all this noise that's going on, and there's a kind of a go, and then a go, and then a no. And I mean, kind of this is, it seems to me this is kind of emergency communication. They're trying to figure out, and, and we're definitely not going, and there's a decision. And I think that, the cut, of course, it's hands off after V1 go, but they got into a decision and she made a decision. It maybe wasn't the right decision, but I think with hindsight, I think these two experienced pilots in hindsight, they had a problem. The two that were in this situation, I think they almost were in a situation that was hard to make the right decision with what they had. We know what she should have done per her training, but I think even asking the staff a direct question, as the vice chairman did, should they have been able to go? That, to me, the response that we got from you all was not an emphatic, absolutely, they would have been able to go, they would have been fine, everything would have been A-okay. That's not really the response that I heard when the vice chairman asked the question.
Unfortunately, with no FDR data, we don't know exactly what the damage was to the airplane. We know that they had the engine power. We know that they had directional controls. And even with the hydraulic loss that they had, that wouldn't have affected any of the primary flight controls. Yeah. So, again, unfortunately, we just don't have any evidence to suggest otherwise.
I think this goes back to what Member Sumwalt had said. The key here has got to be training. I mean, they did not know what they were dealing with. I think they would have, if they had had an engine failure, that would have been a much easier cut, and it would have been much easier for us to say, wrong decision, right decision. And I think they didn't know what they had, and until you train people and give them cues as to what it's going to feel like, I think you're going to continue to have over half the pilots make the wrong decision about airplanes that could fly post V1.
I agree with the chairman that this is not an issue of not having a lot of flying time in the airplane. I think that if she had more time, we may have had the same result. And I'm speaking from experience of somebody who sat in the left seat of an airplane faced with high-speed reject, and I also wavered. I had about 2,500 hours in an airplane. I would say that I was hopefully not overly confident, but I was not underconfident either. And I hit birds. I pulled the power back initially, and then I pushed it forward, and then I finally pulled it back. And I don't think this is necessarily a function of not having a lot of time in the airplane. As the chairman pointed out so aptly, we had very experienced pilots in the Orlando situation. And did they waver? We don't know that. It was not an accident, so we don't know that. So, just exactly what we've said several times, it does go back to the issue of preparing people better to deal with it. Dr. Wilson, you're probably familiar with the Rasmussen's taxonomy of skills-based behavior and rules-based behavior and knowledge-based behavior. And when people are in knowledge-based behavior, which means uncertainty, do they do very well, generally speaking?
Not usually.
Not usually. So we have to get them closer to get them out of that knowledge-based, put them into the rules-based or into the skill-based behavior. And when something scares the hell out of you in the middle of the night, you don't necessarily know how you're going to react unless you've been trained accordingly. And that's why it's so important that we have realistic training that has the appropriate sound and the appropriate motion cueing. So that leads to my second question, and I don't know if, Dennis, if you're here to answer this question or not, but I did, you and I had a conversation a couple of weeks ago with some folks in the training business about the FAA. There's being discussions in the FAA regarding conducting some training in simulators without motion. And here we are, we're issuing recommendations that are calling for greater fidelity with motion and cueing. And can you tell me what is being discussed about possibly saying that motion is not as effective as we think it is?
Well, yes, there has been some discussion based on some research that has been done at primarily at Volpe, though there was also older research done by the military that showed they took 2 sample pilots groups. One group they put through a fixed base simulator, and one group they put through motion base, and they brought them together in a common setting, and found that the results were the same. That was primarily for an engine out. Also, there has been some work more generally in training with basically it was equivalent to a level D simulator, fully up, except it did not have motion. And they did some, again, took some students through that, and both were both the motion and the non-motion students were successful. So that was the basis of the non-motion, not necessarily being, successful and needed for positive transfer of training. The other side of the argument, and again, there's been a considerable discussion in the simulation community on this. One of the other things that happens is the motion cue. Well, typically when we're talking about motion, there's two types. I mean, there's the motion onset that usually has a motion onset and a washout. But the motion is detected by the pilot sooner than the visual. Then as soon as you have the visual, you'll see the motion, or you'll feel the motion, react to that, and then the motion of the airplane is then reflected in the visual motion, and you don't realize that your actual motion is being washed out. The other thing you have in the takeoff, you usually don't discuss the sustained genes, but in a takeoff situation, obviously you're actually tilting the cab of the simulator up, and then to give you a feeling of motion of G's in the back of your in your back, that indicates you're accelerating. And of course, your visual is not showing that discussion. So as far as you know, you're accelerating. So, but that's a longer term motion, and I don't know that. I think some indication in training that that's not necessarily transfers too well to requirements, but it's certainly faster if you're slowing down, like you would be in this case. The acceleration is instantaneous if you can get it. But whereas the velocity, it of course takes time to integrate it in the visual scene. For most everything else, it's faster. I've talked long enough.
No, let me ask you this. So the long and the short of it is we're asking for realistic sound and motion cueing, but here we've got a group of people that's saying, well, maybe we don't need motion. So that's kind of what my concern is. I want to know. Is the FAA proceeding with this? If we can get better quality of training without motion, then maybe that's something that should be looked at here. But in this RTO scenario, you've got 2 things that I think that startle you. You've got the noise, the loud noise, the banging, the shuddering, the rattling, and then you've got, I suspect, a motion associated with the airplane swerving. And so how are we going to create this realistic simulation without motion cueing?
Well, I think motion cueing comes in different forms. In a fixed space simulator, if you want to proceed with that, you do have the option, and I think most of them do have the vibration seat for picking up the motion cueing of high frequency, like the vibration that you would see here. I mean, I think primarily you'd have obviously very loud, and the current Part 60 mentions the sound, and and that's fairly easy. And then the motion, the vibration is high frequency, and that can be picked up on a motion seat. Then of course you've got the tendency to swerve if you don't do anything about it. Obviously there's a motion in the airplane modeling needs to do that, and you'll see that visually in a motion.
Okay, thank you for coming to be able to answer those concerns that I had. I appreciate that. Thank you.
Vice Chairman. I'll just follow up on a couple of areas, and I think I kind of want to go back to this issue of the data. If we're looking at data to try to help guide what's coming up, I think the chart that was up in that video that's almost 20 years old, and it was also included in our 1990 Special Investigation Report, stated that almost as many events occurred because of tire failures as engine failures. So if we're looking for the data to help give us direction about what we need to address, and we're looking at accidents to help give us examples of that, we had the 1990 Special Investigation Report. We've had work that's been done by a lot of manufacturers to look at accident information. Why wouldn't the FAA want to introduce this type of training into the simulator? I think, you know, I understand every time we add something into simulator training, it's a zero-sum game. We might have to lose something. But when you look at the data and you look at the numbers and you look at the frequency of this type of event, it's not a de minimis thing. It's not a one-off. The data's there. If we're going to use data to help us determine what decisions we should be making in the aviation community, why wouldn't FAA or the industry draw on this type of data?
I might suggest that it's possible that what we're seeing is just a very slow evolution in the area of the importance of V1 cut training. It could be that years ago in the industry, engines were a lot less reliable than they are now. And the bigger threat for what might cause you concern in the course of your takeoff roll might have been a much higher frequency of engine failure events. So the industry developed this mindset, and the V1 concept tied that to what at the time was the biggest threat, which might have been loss of an engine, and entrenched that methodology of training into the piloting community. Round about the 1990 study, though, perhaps we were seeing now that engines have become more reliable. Maybe the incidence of tire failures wasn't becoming more frequent, but maybe the number of engine failures was coming way down, and those two were beginning to catch up. Certainly the circumstances in the industry now tell us that that threat from tire failures is very important and needs to be integrated into that V1 cut training.
Well, Mr. DeLisi, that was a nice effort to try to defend the decision-making process, but I'm looking at our 1990 report, which is 20 years old, and this same chart that was in that video was actually produced by the Boeing company, and it's RTO accidents and incidents involving commercial jets from 1959 through 1988. So I think that the quarter of engine propulsion anomalies and the quarter of wheel tire problems is something that's been well known for at least 20 years, and it's based on data that's much older than that. And so I think this is just one of those examples where we're having to relearn through accident investigations lessons that we've learned before. And we know that if they don't heed the recommendations, we will be back again looking at the same type of accident, having to make a similar type of recommendation. I'm going to move to an area that I know that everyone's expecting me to raise, and that's fatigue. Remember someone else mentioned that they were in an unfamiliar airport near midnight, but one of the issues that came up when we discussed the Colgan accident report when fatigue was raised, that the crew did not make errors that were consistent with fatigue, misspeaking, not catching errors, confusion. And I think that in this accident, we see a crew who gets lost on the taxiway because one hears an instruction, another hears a different instruction. They don't get that straightened out. They end up having to get revised taxi instructions. They also have a disparate perception of whether or not they were given the authority to cross a runway. They don't fix that. There are briefing errors in the briefing that's given by the captain, some that are not corrected by the first officer. This crew had certainly an opportunity to rest, but that doesn't actually mean that they did rest. And it's near midnight when they're taking off, and I know that they're going to California. How long was the expected flight to California? 4 or 5 hours?
It was between 4 and 5 hours.
So that would put them, potentially getting in 4 or 5 a.m. in the morning. I just think that I've talked with the staff about this. I think even with the diphenhydramine that was detected in both the first officer and the captain, we've long had concerns about the sedating effects of over-the-counter medications. I think they're errors in the short period of time that we have them on the CVR. They have errors that are present and could be consistent with fatigue. I think the presence of the medication for both of them is an issue too. So I think that the staff, does not have the confidence to pursue this issue, but I think that it comes up again and again in our accident investigations, and I wonder if they had this accident on landing at 4 or 5 a.m., would we have felt any different?
Well, when we looked at, I'll address the diphenhydramine first. When we looked at the diphenhydramine, the levels that we found were actually fairly low. It's possible that there were some effects due to the diphenhydramine, but we really don't know how much they took or when they took it or why they took it. And when we looked at some of the research, we found a study that looked at individuals who took a max dose of diphenhydramine, which would have been 2 pills or 50 milligrams, and mental impairment and reaction time, increase in reaction time was only found in about 2 hours after they took the maximum dose. And the levels of diphenhydramine that was found in the blood was about twice that of what was found in our flight crew. And they also looked at subjective reporting of sleepiness, which lasted for about 6 hours after taking this maximum dose. And the lowest level of offset of when individuals no longer felt sleepy was about 0.03. So given that the levels of our flight crew were around 0.03, 0.036, we didn't feel that they were having any mental impairment or increased reaction time due to the diphenhydramine. But again, obviously there are individual differences, so and each individual will react differently to it, but based on the research that's out there, we don't think that there was any significant impairment due to the diphenhydramine. And when we looked at fatigue, we really had limited information as to the crew's sleep and wake times. All that we had to go off of was cell phone records. So we know that the flight crew had the potential to get upwards of 9.5 to 9 3/4 hours of sleep the night before. We don't know what their normal sleep or wake times were when they were off duty, so we don't know whether there was any sleep debt. But we do know that in the 2 previous nights before this accident, that they had been awake based on cell phone activity up until about 1 or 1:30 in the morning. So this wasn't a time that was falling during their normal sleep period, and we know that we do have a peak in circadian rhythm right before our normal bedtime, so we would think that this might have been a time when they were more alert.
But yet they made mistakes that were consistent with fatigue.
We did look at that, and we also know that that for 135 on-demand operators, they are not required to have CRM training, and a lot of the errors that they made were consistent with poor CRM. And while they did receive some training, we really don't know what they were trained on or how they were trained on it to know whether it was really effective.
I think the issue of the over-the-counter medication is a concern because we have, for many, many years, recommended that Department of Transportation wide that they provide information about what over-the-counter medications are impairing and what medications are okay and what dose. And I saw that just this past week the FAA came out and has permitted pilots who are diagnosed with depression to now be able to fly under certain circumstances. But the point is that a lot more of our accident investigations have involved pilots that are impaired by over-the-counter medication, not impairing medications that are prohibited. These are things that they don't know what they're allowed to use and in what dosage, and we see this across the mode and across the board in all modes of transportation. And they have got to provide some guidance for operators. It makes absolutely no sense. We have 2 operators, 2 pilots here who both were consuming something that we know has a sedating effect. They need to help pilots understand what the benefits or what the cost of this medication is as far as their performance. Member Sumwalt?
Thank you. Regarding the actual rejected takeoff performed by the captain of this airplane, I was reading in one of the submissions, it appears that the thrust was brought all the way back pretty much to the stop based on the signature of the sound spectrum. Is that what you understand it?
Yes.
So it's brought all the way back and then back up again and then back again. So
Correct.
So at least in my wavering, I only pulled it back a little and then pushed it forward a little. But yeah, I was surprised to see that she pulled it all the way back. It was clearly, I'm going to stop, no, I'm going to go. It wasn't a hesitation. It was a period of indecision. The brakes were applied how many seconds after the thrust levers came to idle, either the first or the second time?
We can't tell that. We have no FDR data to tell when the brakes were applied.
Okay. Now, one of the submissions pointed out that a squealing that would be associated with the brakes came in 9 seconds after V1. Now, of course, the takeoff wasn't initially the unraveling of the tire didn't occur until about a second or a second and a half later. But okay, so you can't tell when the brakes were applied.
Yeah, the squeal would be associated with maximum brakes, and it's just a characteristic of the airplane. But if she had been pressing the pedals at a lighter pressure, she may not have had the squealing, but had been on the brakes. We just don't know without the FDR.
The rejected takeoff procedure calls for the brakes to be applied at what intensity? Maximum. And so what you're saying, Mr. Swaim, is that we didn't get the squealing until about 9 seconds later, and they could have been on the brakes, but at a lesser intensity than maximum. Do you agree with that?
Yes, sir.
Okay. So not only was the takeoff rejected after V1, but after the rejected takeoff was initiated, the brakes were applied at full intensity much later. The first step of the RTO procedure is what?
Throttles to idle and then max braking.
Nope, it's brakes first.
Oh.
Let's get it right. Do you agree with that, Captain, too? It's simultaneous, but brakes are listed first.
Yes.
Then thrust levers, then spoilers, and then, if required, max.
That's correct, but as you say, they're all done together. I mean, they're coming back and applying brakes. Yes.
Thank you.
But you're correct.
I want to go to a completely different topic, and this concerns the issue of the uncertainty regarding the taxi instructions. Do we know how many sets of airport charts this crew had? Did they have one set of JEPs, 2 sets? Do we know?
It seems like I recall they had one set, but I'll be honest with you, I'm not positive of that.
It
I
appears,
can find out.
It appears from listening to the CVR and reading the CVR transcript that the FO, that the captain does not have a chart in front of her. That's what it appears.
Yeah, normally in this airplane, there's not enough room up there for a lot of charts. And
I understand that.
Like I say, I think it's in the back of my memory that there was one set. But
the board has issued recommendations for both pilots to have approach charts coming out of a couple of accidents, all involving small cockpits for 135s. The first was in an accident that happened in 1985 in Bar Harbor Airlines. It was a Beech 99, so not a very large cockpit. We came out again and looked at that in a GP Express accident in June of 1992. Again, a C-99, Beech 99 cockpit, fairly small cockpit, about the size of a King Air cockpit, which is actually larger than the Lear. We then came out and reiterated that coming out of an accident, a Jetstream J31 in Hibbing, Minnesota, which was also a Jetstream, pretty small cockpit. We've come out and we've talked about repeatedly the need for both pilots to have charts in the cockpit. Those were closed to unacceptable action. The advisory circular, AC 120-74A, which came out in 2003, deals with Part 91, 121, 125, and 135 flight crew procedures during taxi operations. In that AC, it says under best practices, it says both pilots should have the airport diagram out, available, and in use. It also says that after the taxi clearance has been received, the crew will agree on the assigned runway and any restrictions in the taxi route. If not in agreement, the flight crew will seek clarification from ATC. We in our investigations, we're very interested in runway safety. Runway safety is not just runway incursions, it's all of runway safety. So it would be good that when we do our investigations that we not only look at those issues that are proximate to the accident, but we look at issues that relate to things that affect other issues of safety. Here the crew didn't have the charts out. The captain didn't know which way to go. She turned the wrong way. She deferred to the first officer. There was a question about should we hold short of this runway, 22. She said it was really 23. He said, well, I think he said cross it. If you've got a question about whether or not to cross a runway, it shouldn't be decided upon between the two of you. At that point, that there's the indecision. It doesn't cost anything to key the mic and say, are we cleared to cross this runway? So my point is that this had nothing to do with the accident, but it was something that I noticed that is related to something that's very important to this board, and that is runway safety. So where am I going on that? It's just that. We need to look at things that don't necessarily affect the accident itself, but deal with things that are important to this board. Thank you.
We're going to take a 10-minute break, and then we'll come back in for the last presentation. We'll now proceed to the final presentation.
The final presentation is combined, beginning with Robert Swaim on the derivative certification, thrust reverses, and he'll be assisted with Captain 2.
I would like to present the technical aspect of how the thrust reversers should work and could fail, leading to Captain 2's presentation about the use of the reversers. First, though, I need to discuss how a certificated airplane may change over time. A type certificate is the legal text description of what a particular airplane is, and it locks the design into a specific set of features. Derivative certification, also known as changed aeronautical products, was intended to allow specific changes that would not require a full certification program. For example, changing the number of seats in the cabin. The Model 24 started the Type Certificate Data Sheet, or TCDS, that became the legal description for all but 2 airplanes in the history of Learjet. After numerous intermediate models, the Model 60 was introduced in 1993 as revision number 59 to the TCDS that started with the Model 24. As you can see, the beginning and end of the product line are not the same airplane, but the TCDS was maintained as the series of airplanes stepped from one to the other. The FAA did require most of the Part 25 regulations current in 1993 to apply to the Model 60, with some exceptions. A primary exception that relates to the Columbia investigation would be in failure analysis for the hydraulic supply to the brakes and of the electrically controlled thrust reverser system. The FAA permitted use of the original 1965 version of the Part 25 1309 regulation that describes what failures to plan for and how to address those that do. This regulation was substantially changed between 1965 and 1993. In short, the 1965 version of the regulation called for protection against single-level failures only and a statistical probability of reasonably probable. The 1977 version of 25-1309 required protection against combinations of failures and a statistical probability of extremely improbable, which is 10 to the minus ninth. The newer version has other improvements, such as for crew recognition of problems that do arise. Regulation 14 CFR 21-101 addresses the process for changed aeronautical products. A 1981 special certification review into some Learjet accidents criticized the process in continuing to use the 1965 version of 25-1309 for flight critical systems. Yet in 1993, the Model 60 was still certificated using the original 1965 version of 1309. In the years 2000 to 2003, the process was changed and greatly restricted from what it had been by the FAA. The exemption initially seems to make sense in how it is stated, but the application can still exempt electronics associated with the thrust reverser system that are in the area of the landing gear. To finish about the certification process, these are photos of the landing gear in a Model 60 on the left and a 45 on the right. They show the differences in protection between the earlier and later standards, including of Part 25-1309. The Model 45 uses protective plating to cover vulnerable parts, and the exposed hydraulics are fused to shut off massive leaks. So now turning to the thrust reverser system itself, when the airplane is on the ground, the engines are at idle, and other conditions are met, the pilots can lift the thrust reverser piggyback lever on the throttles to deploy the reversers, diverting the engine exhaust as shown on the right. The term reverse means that the air from the engines is redirected, not that the engines actually change direction of rotation. To change the direction of thrust the engines produce, the blocked exhaust flow is then redirected as shown by the blue arrows. This creates aerodynamic drag to slow the airplane and assist the brakes. The Model 60 was certificated to fly without the thrust reversers, and maintenance can even lock them shut for 10 days. This 1993 model was the first Learjet to have electronic engine control, and as a result there is no mechanical feedback in the levers about where the reverser doors may be at the engines. The thrust reversers have a set of 3 annunciator lights for each engine, as shown in the upper photo for the left and right side. When on the ground with throttles at idle and the logic criteria met, the green TR arm annunciator illuminates as shown here. When the pilots lift the piggyback levers slightly, further movement is blocked until the reverser doors on each engine are fully deployed. So during transition, this set of lights will show for about a second or two. Once the reverser doors are fully deployed, the arm and deploy annunciators illuminate, as seen here now. At this point, the piggyback levers are freed, so the pilots can pull up to command more than idle thrust. For designers, the worst case is with respect to thrust reversers, would be to have one open immediately after takeoff, giving the crew a loss of thrust and diminished control while at low airspeed. So Learjet's fail-safe concept, including for a failure of a squat switch, was to stow the reversers. Now, to get the reversers to deploy, the airplane has to be on the ground, as sensed by the squat switches. The throttles have to be at idle, and the system needs to keep passing self-checks, such as having the squat switches not in the air mode. After a landing accident at Troy, Alabama, the squat switches on a Model 60 were broken by hitting deer. The reverser stowed and the airplane went off the end of the runway. The Columbia accident airplane incorporated a sensor change that had been developed after the Troy accident. Unfortunately, the change neglected to address the rejected takeoff condition. We have a video to show normal reverser operation. Please note the annunciator lights in the upper left, the hand on the reverser levers, and the reverser door movement at the engine. Try to watch for the arm and deploy lights on the glare shield as there's movement. See the lights? And we will repeat it for you to try to watch for those lights. They're small. We'll now show the system stow for a simulated failure of a squat switch by using an orange test box. The test begins with the test switches in ground mode, goes to air mode, then the annunciators flash and go out as the reverser doors stow. At the airplane, we could hear the engine speeds increase to flight idle from ground idle. Watch the lights. And they're out. This concludes the technical aspects about the reversers and certification that got us here. Captain 2 will continue with the operational and crew aspects. Thank you.
Good morning. Investigation into the Columbia accident revealed some operational deficiencies with the Lear 60 thrust reverser system. These deficiencies can be best understood with a brief recap of the Columbia accident sequence. Once the captain decided to reject the takeoff, she began the rejected takeoff actions by retracting the engine power levers to idle and then pulling up and back on the reverse levers to command reverse thrusts. As Mr. Swaim indicated, damage from tire debris subsequently resulted in the reversers stowing. Staff believes that when the reversers stowed, the captain, who was the flying pilot, did not initially recognize that she no longer had reverse thrust. The investigation determined that pilots had minimum visual cues and no oral cues, that even though the reverse levers were in the reverse thrust position, the reversers had stowed and the engines were now producing forward thrust. The only visual cockpit indications of this change were 3 small annunciator lights located on each pilot's side of the forward glare shield. Specifically, the TR deploy annunciator lights would have gone out immediately when the reverser doors began to stow, and the TR unlock and TR arm annunciator lights would have flashed momentarily as the reversers were in transit to the stowed position, and then they would have gone out. If the pilot did not notice the disappearance of the TR deploy lights or the momentary illuminations of the TR unlock and TR arm annunciator lights and recognized the emergency condition they indicated, there were no other visual cues in the cockpit to indicate that the airplane was now producing forward thrust. While attempting to control and stop the airplane, the pilot would have to make a critical decision based on a correct interpretation of a lack of annunciator lights. There were more than 70 similar size indicator lights located in that area. Staff is concerned there were insufficient visual cues and no oral cues to allow pilots to recognize that an inadvertent reverser stowage had occurred. The board has issued recommendations in this area, and the FAA has responded that they have formed a team of specialists to assess the underlying safety issues. Staff proposes reclassifying these recommendations. When the air-ground switch failed and the reversers stowed, causing the system to revert to forward thrust, the accident airplane's reverse power levers remained in the reverse thrust position. This lack of lever movement deprived the pilots of a tactile cue that would have alerted her to an emergency situation of inadvertent thrust reverser stowage. The board has issued recommendations in this area, and the FAA has responded that they have formed a review team to assess this issue. Staff proposes classifying this recommendation. To compound the problem during the rejected takeoff, the pilot had the reverse power lever in the up and full back position, leading her to believe that she was commanding reverse power when actually the system was delivering forward thrust. The only way to reduce the forward thrust under this emergency situation was for the pilot to move the reverse lever to the forward idle stowed position. This would be a counterintuitive action during a rejected takeoff. The investigation revealed that most Lear 60 pilots that were interviewed had encountered an inadvertent thrust reverser stowage situation during simulator training, but usually this occurred during a landing scenario. An inadvertent thrust reverser stowage training event was infrequently or rarely demonstrated during a takeoff scenario. The board has issued a recommendation in this area, and the FAA has responded that they have issued a safety alert for operations, or a SAFO, concerning training. Staff is concerned that SAFOs are not mandatory and proposes reclassifying this recommendation. This concludes my presentation.
That's all the staff presentations. Thank you. Member Sumwalt.
Captain 2, in the transport category airplanes that you flew, if a thrust reverser retracted, stowed, and you had the thrust levers, the reverse thrust levers back, and you were pulling for reverse thrust, in the airplanes that you flew, what would happen to the reverse thrust levers?
The thrust reverse lever would come forward to be in agreement with the position of the.
It would come forward to be in agreement. This airplane didn't have that feature.
That's correct.
Now the Lear 45, can you explain to me how it would have reacted in a auto stow situation, in a situation where the thrust reversers retracted and you were commanding for reverse thrust?
Let Mr. Swain.
Yes, sir. Lear 45 has a solenoid to bring those levers down, even though it's still an electronic controlled engine.
So, okay, good.
It works the same as the older airplanes where there was a teleflex cable from the reverser to where your hand is holding. That's all your mechanical systems. There's a cable actually going from the cockpit to the reverser. The later airplanes have a solenoid that mimics the cable electrically. This airplane and a few others are the exceptions that do not.
Okay. This airplane, the Lear 60, and what other airplane? It would be the Hawker 1000.
Yeah, it seems to me the Hawker 1000, and there was another that came up. The Hawker 1000, absolutely, because it was the subject of a recommendation that we put in. But it seems to me there's another, and I don't remember off the top of my head.
Okay. Thank you. Now, while I'm talking about the Lear 45, I want to ask a question about it. As I understand it, all Lears between 1966, 65 or 66, and 99 were certified under TC 10 Charlie Echo.
That would be the type certificate for all but the Model 23 and the 45. The 23 was under CAR 3.
Right.
And the 45. Okay.
But the 45 was certified after 99, after 96. So between 1966 and 99 or 96, all the Lears were the 24, 25, 35, 36, 55, all of those, 31, all of those were done under 10 Charlie Echo. But all of a sudden, when we came to the Lear 45, that didn't fall under 10 CE, did it?
No, sir.
Why not?
It was a larger airplane, and by that point, the FAA had internally picked up that they were going to change 21101, the certification process, the derivative process. They internally knew that was going to change, and they had to restrict things, and the 45 was a new piece of paper.
Okay. Now, while we're talking about comparing the Lear 24, which was the first airplane that was certified under 10 CE, TC 10 CE, and the Lear 60, which was the last Lear to be certified under 10 CE, let's look at the difference. In terms of max gross weight, the 24 maxed out at 13,000. The 60 maxed out at 25.5. Max seating capacity, including pilots, for the 24 was 8 versus 10. That's not a huge deal. Max altitude for the 24 to 41,000 versus 51,000 for the 60. Range 1266 for the 24, over double that for the Lear 60, 2768. The engines for the Lear 24 were conventional controls, whereas when we get into the Lear 60, they're FADEC, controlled by a computer. Cockpit for the Lear 60, Lear 24, it's an analog cockpit. For the 60, it's a glass cockpit. As you pointed out, the fuselage and the wings were different. We're not just talking about a longer fuselage like some airplanes do. You take a 737, 200, 300, 400, it gets longer and longer. What we did here, what happened here, it's a total different barrel. Instead of it being perfectly round like that, now it's an oval, an oblong thing that somebody my size, it would be considered stand-up headroom, whereas you'd have to crawl almost through a Lear 24. The wings were different. There are huge differences between these airplanes. Is that correct?
Absolutely, sir.
Huge differences. And yet the FAA allowed it to continue to be certified under 10 CE in spite of all of those differences. And those are just ones that I was able to pick up on. There's all kinds of engineering issues related that I don't even know about. You had something you wanted to say?
Yes, sir. The FAA did not base everything in that original 1965 certification. They did update as they went along. For example, the wing that you point out, that was based in a 1979 certification that followed the big changes that came in 77, regulatory changes that happened in 77. So the wing, yes, it was a totally different wing. They'd gone from the tip tanks and the smaller wing to the Longhorn wing with the winglets. But when the 60 was certificated in 1993, the type certificate specifically says it complies with the most recent Part 25 regulations with these exceptions, and it listed exceptions, 13109 being one of them. 25.1309 being one of them.
Okay, thank you. Now, I understand that the Lear 60 certification was done without the use of thrust reversers, and I realize that may mean that it was done without taking landing credit for the use of thrust reversers, but in fact, if you read on page 54 of the report, here's what it says. It's easy for me to find. Yeah, it says the certification and flight test for the Learjet 60 were conducted without the use of thrust reversers and without reverser credit for calculating takeoff and landing runway length. What does this exactly mean without talking about not taking credit for the takeoff and landing length? I understand that. Does this mean that they completely disregarded the fact that thrust reversers were on this aircraft?
Absolutely not. What it means is that when they did their performance work to determine how well the airplane performs and to design for that, the thrust reversers were an assistance to reduce wear on the brakes. They weren't meant as part of the actual stopping capability of the airplane and coming into some airport. They reduced the wear.
Okay, but what I'm asking is, and that deals with takeoff and landing distance, what I'm asking is, did the FAA consider the fact that this airplane had thrust reversers on them and had this non-feedback mechanism to follow up on the stowing of the thrust reversers? Did they even consider that?
Yes, sir. There was a full failure mode and effects analysis done. What we picked out of there is that it addressed the different requirements of the regulations, the ACs and so forth. The one detail that we could pick out actually, was where it would say the crew has to be able to recognize a fault. The regulation and the AC don't say in a certain amount of time. And so it's a very slight thing, you would think, or a subtle detail, but it's something that's not reflected when you look at those lines in the FMEA.
Okay, thanks. It may be that this thanks for that explanation. It may be that this statement is a little misleading, since it says certification and flight test for the Lear 60 were conducted without the use of thrust reversers.
Learjet did also do flight tests and landings with considering thrust reversers. They actually flew an airplane with an open reverser to a successful landing and stop.
Okay.
So they did fully certificate and properly certificate the thrust reversers by those aspects.
Okay. I still maintain that could be a little misleading the way it's written, but I'm not going to nitpick the report. Thank you.
Vice Chairman. Okay, so Mr. Swaim, in 1993, with kind of classifying this as a derivative design, they were able to incorporate some of the 66 applicable standards, but also some of newer standards, some that kind of had changed along the way. How did they determine which area is subjected to the newer standards and which areas get to be grandfathered under the older standards?
Typically, the way the FAA does that is by looking at what has a reasonable, and I realize that's a wishy word, but what has a reasonable similarity. We found many places in the certification documents that said similar to, previously used as, those kinds of words in the certification documents. So from that point, it really comes down to the specific system or feature you're addressing for how that interpretation would have been applied by the individual DER, designated engineering rep, or the FAA inspector who was looking at it directly at that day, that time.
And in the past, I've heard something, a discussion of this referring to new or novel designs. And so are they looking for changes that are different?
There are definitely some of those, including here. The 1309 requirement that we're talking about going back to 1965 in the type certificate data sheet, the TCDS also exempts from that the EFIS, the electronic flight instrumentation and associated parts, and says that those can be up to or need to be required to at least 1977 requirement. So 1977 is when the failure requirements of 1309 were improved greatly, and the EFIS was held to the 1977 requirement, which was a lot more stringent than 12 years before.
Okay, but let's go back to just talking about the thrust reversers. They were only required to comply with the original type certificate standards. Is that correct?
There's a fine line here in the reversers as mechanisms. There's a part for those, but as far as 1309 and failure modes, that aspect was back to the 1965.
Okay, but when they talk about things that are similar to or like the previous, wasn't this the first Lear that had electronic controls for the thrust reversers?
Yes, ma'am.
Why wasn't that considered different or new?
That's the question we didn't ask.
So in 94, and this is talking about one of those test flights, in April of 94, there was an accident during landing involving one of the prototype flights. The airplane landed with suspected flat tire. The pilot's application of thrust reversers produced no deceleration, and the airplane went off the end of the runway. Post-accident exam found that both right main landing gear tires were flat and that the right strut was damaged. So they're doing this test. Why wouldn't maybe that have flagged then that they had a malfunction? I get it that they're not taking credit for the thrust reversers in landing, but they've identified a failure here.
They identified the failure in the flight test. And what they did with it is they figured that it was not something that would come up by the statistical criteria, that it would be a common thing. And so they put it in the abnormal procedures. Now that was changed after the Troy, Alabama accident, and they made that a memory item. They moved the inadvertent stow procedure into a memory item, boxed it, and put more emphasis on it.
Okay, and the statistical likelihood, is that 10 to the minus ninth? Are we talking about some other statistical likelihood?
That's what I'm talking about.
Okay, so when we're trying to figure out about the statistical likelihood of something happening, and then something goes into service and something happens, how do we know if it's within the parameters of the statistical likelihood? We know that there was a 98 incident during a rejected takeoff, a Lear 60 at Dulles. According to the pilot's report, both right main landing gear tires failed during the takeoff roll. Damage to the tire and brake assembly led to several severed hydraulic brake lines and squat switch wiring. The thrust reversers stowed during the attempted RTO, and they went off the left side of the runway. Would that have been a 10 to the minus ninth event? And, the question that I have is, when does the certification process recognize that it's maybe failed or made a bad assumption? If something's not supposed to fail and it fails, do we have the data to show how much exposure there is and how often the failure is occurring?
It comes back largely, to what you brought up before about how much data is available. Now, you happen to pick a great example with the Dulles incident. There's one that we picked out of the NASA reports, but we did not see the same incident in going through the Learjet information. So we were talking about SDRs and people not reporting items. Well, there's an example that we know the airplane had this incident, but we don't see the record in the Learjet company knowledge base and the FAA's knowledge base. It came out of the NASA ASRS. If Learjet or the FAA don't know about it, they can't assign that or reassess their 10 to the negative ninth, for example, number. Yes, it's a number of 1, not 10 to the minus ninth, 10 to the 1 for that Dulles event, but not if you don't know about it.
Well, and even beyond that, we have to have the exposure data to understand what the denominator is. And so how many hours they've been in flight, how long they, kind of what do we know? And I think that's kind of again points to the challenges with some of the data. If they had applied the standards that were in effect in '93 for thrust reversers, certification of thrust reversers, do we think that they would have caught this failure mode?
I think the answer is the rejected takeoff criteria was not considered, even after the 2001 accident in Troy, Alabama. So it's not even a matter of '93. It's a matter of not recognizing that this mode of flight was left out of the failure mode evaluation.
Thank you. Member Somewhat.
Yeah, the chairman mentioned that in '94 there was a prototype Lear 60 was involved in a situation where the aircraft went off the end of the runway after failing tires, and then we had the Troy, Alabama event. And what was Lear's response to those events? What did they do after that?
Well, it's, again, a series of steps. After the flight test airplane, they put the procedure in the pilot's handbook. They didn't know about the Dulles incident that happened between the Wichita and then Troy, Alabama. After Troy, Alabama, the FAA was happy with moving that to the emergency procedures, and Learjet on their own initiative went farther and put in the change in sensor hardware electrics to try to lock in that ground mode.
Now the change in the sensor, where the airplane takes wheel spin up, would that have prevented this Columbia accident?
No, actually, this airplane had that change incorporated already.
Right. So it didn't affect this particular situation because the airplane has to be in the air for at least 2 minutes, and you have to have wheel spin up for 50 seconds. Explain to me what that situation is.
Basically, the airplane has to get into the air for 2 minutes to reset the system, and then once it touches down, you get the squat switches closing, you get the wheels to spin up, and with the two of those together, it locks in the logic for 50 seconds. They figure that within that 50 seconds, you're going to use your reversers, come to a stop, and you won't need them again. So that's the logic of the 2 minutes into the air and the 50 seconds on the ground. If you don't get to that 2 minutes in the air, which is our case here, then you don't reset the system, and you don't have that safety factor, the wheel speed, for the rejected takeoff.
Okay, thank you. Now you mentioned that after the '93 event, they put Lear put a procedure in the pilot's handbook. Is that correct? But they didn't make a hardware change.
Not at that point. It was a very unlikely problem, they felt.
Okay. After the 2001 event, they came out and they made a hardware change. Okay, now in the system in the safety order of precedence, the first thing you should do when you have a problem, you should design for minimum risk. This is right out of the FAA System Safety Handbook. Design for minimum risk. The next level is that you should incorporate safety devices. The third thing you should do is provide warning devices. And the very last thing, intervention strategy you should employ would be to develop procedures and training. So here's a case where Lear went to, and the FAA approved, the very lowest order of corrective action. They said if it doesn't work right, here's what the pilot should do, instead of coming in and designing a fix that would have eliminated the problem in the first place. So I have no further questions.
I just have one last comment. I think we sometimes have a tendency to be very hard on failures because in some ways that's our job. We're trying to figure out what went wrong to prevent it from occurring again. We did have a few things in this accident that did go right. I did think that it was very impressive that the first officer in that chaotic environment did recognize that he needed to shut those engines down, that what was going on in there was not what they were commanding and not what they wanted. And so he did recognize during that brief sequence what was happening, just didn't have enough time to execute and distance to slow it down. He also got on the radio to ATC to tell him to roll the equipment that they were going off the end. I mean, that was to me also in a crisis moment. He was showing, consistent with his training, that he was aware of what was going on. I think the air traffic controller on duty almost midnight was also paying attention, and we are often critical when people are not on top of their game. The controller noticed that they had turned the wrong way when they were coming out for their taxi. He recognized it and he gave them amended taxi instructions, helping them get to where they needed to go. The controller was also watching them as they were going down the runway, noticed the sparks coming off the aircraft, and there was a quick notification to the responders, the emergency responders, to roll the equipment. And so I think in the end, we still had a tragic result and not what we wanted, but I did want to mention that our team did identify that there were some actions from the air traffic controllers that are to be commended. So with those comments, any further?
No, thanks, Madam Chairman. I'm glad you mentioned that because I had actually meant to make a comment about the first officer's performance, and you are correct. He shut down the engines, and I think another thing that I noticed was that within 4/10 of a second after the beginning of the rumbling associated with the tire failure, within 4/10 of a second, he had already stated go. And 6/10 of a second after that, he said, go, go, go. So he was in that go-minded frame of reference that we say you should be in after V1 unless aircraft control cannot be positively determined. So I'm glad you mentioned that. I intended to do the same. Thank you.
If there are no other comments, does staff have any other comments or presentations?
No, ma'am.
Okay. Dr. Meyer, will you read the findings of the investigation? If any board member has any questions or comments, please let me know after all of the findings are read.
Yes, ma'am. We're proposing 26 findings resulting from this investigation. Number one, the captain and the first officer were certificated and qualified in accordance with federal regulations and the operator's requirements for the 14 Code of Federal Regulations, Part 135, on-demand flight. Neither pilot had any previous aviation accidents, incidents, or enforcement actions. 2, the accident airplane was certificated and equipped in accordance with the regulations that applied to it as a changed aeronautical product. 3, there was no evidence of any pre-impact anomalies or distress that would have prevented the engines from producing power. 4, there was no evidence of any flight control anomalies. 5, the following were not factors in this accident: tire design, tire manufacture, or damage to the exterior of any tire. 6, although post-accident estimates indicated that the airplane's maximum gross weight may have been exceeded by up to 300 pounds, there is no evidence that the weight and balance issues contributed to the accident. 7. There was no indication that the captain's understanding of the rejected takeoff criteria was deficient, thus the captain likely misspoke when she incorrectly stated the criteria in her pre-takeoff briefing. 8. The captain's uncertainty as to whether to continue the takeoff suggests that her initial action to reject it did not result from a perception that the airplane was uncontrollable and could not fly. 9. In the absence of evidence that the airplane was uncontrollable, the captain's execution of a rejected takeoff for an unknown anomaly after the airplane's speed had passed V1 was inconsistent with her training and standard operating procedures. 10. The accident airplane's uncommanded forward thrust, which accelerated the airplane at a time when the flight crew commanded full reverse thrust to decelerate the airplane, increased the severity of the accident because the uncommanded forward thrust substantially increased the airplane's runway excursion speed. 11. All 4 main landing gear tires on the airplane were operating while severely underinflated during the takeoff roll, which resulted in the tire failures. 12. The accident airplane's insufficient tire air pressure was due to Global Exec Aviation's inadequate maintenance. 13. Some operators are not sufficiently aware of the appropriate tire pressure check intervals for the airplanes in their fleets and are operating their airplanes with tires inflated below the aircraft maintenance manual replacement specifications. 14. Aircraft maintenance manual AMM formats that refer to tire pressure checks as guidance information rather than required maintenance intervals, and the lack of standardization of AMM formats with respect to the location of tire pressure check interval information do not provide sufficient emphasis on the criticality of checking and maintaining tire pressure. 15. The Federal Aviation Administration's legal interpretation that checking tire pressures on a Learjet 60 is preventive maintenance has an unintended negative effect on the safety of 14 Code of Federal Regulations, Part 135 operations, because according to the provisions of 14 CFR 43.3, a Learjet 60 pilot who is allowed to perform preventive maintenance, such as tire pressure checks, on the airplane for a flight operated under 14 CFR Part 91 is prohibited from performing the checks on the same airplane for a Part 135 flight. 16. Tire pressure monitoring systems which enable flight crews to easily verify tire pressures provide safety benefits because the pressure loss rate of aircraft tires can result in tire pressures below acceptable operational values within only a few days, and such underinflation cannot be visually detected by flight crews. 17. Learjet system safety analysis and the Federal Aviation Administration's review of the Learjet 60's thrust reverser system modification and revised crew procedure were inadequate because they failed to effectively address an unsafe condition for all phases of flight, specifically uncommanded forward thrust during a rejected takeoff. 18. Had the Federal Aviation Administration adopted the procedures described in SAE International's SAE ARP 5150, Safety Assessment of Transport Airplanes in Commercial Service, to require a program for the monitoring and ongoing assessment of safety critical systems, the FAA may have recognized, based on problems reported after previous incidents and an accident, that the Learjet 60's thrust reverser system design was deficient and thus may have required appropriate modifications before this accident occurred. 19. The Federal Aviation Administration's 1993 certification of the Learjet 60 as a changed aeronautical product, which allowed the airplane's equipment, systems, and installations to conform to some regulations applicable to the original 1966 certification, did not ensure the highest level of safety and allowed for deficiencies that would not likely have been present if the current regulations had applied. 20. The accident pilots would have been better prepared to recognize the tire failure and to comply with the takeoff if they had received realistic training in a flight simulator on the recognition of and proper response to tire failures occurring during takeoff.
Dr. Meyer, was that continue with the takeoff?
Yes, it was. Let me just reread that one. 20. The accident pilots would have been better prepared to recognize the tire failure and to continue the takeoff if they had received realistic training in a flight simulator on the recognition of and proper response to tire failures occurring during takeoff. Thank you. 21. Because 14 Code of Federal Regulations Part 135 does not require that pilots in on-demand turbojet operations have a minimum level of experience in airplane type, the pilots may lack adequate knowledge and skills in that airplane. 22. The captain's indecision in responding to the anomaly and her failure to follow standard operating procedures was the result of a combination of poor crew resource management skills, limited experience as a pilot in command in the Learjet 60, and, during the accident sequence in particular, her less than confident and assertive leadership in the cockpit. 23. Although flight crew impairment related to diphenhydramine use or fatigue is possible, there is insufficient evidence to determine to what extent, if any, diphenhydramine use or fatigue may have affected the captain's and the first officer's performance. 24. The captain's passenger safety briefing contributed to the survival of 2 passengers. 25. The tire design and testing requirements of 14 Code of Federal Regulations 25.733 may not adequately ensure tire integrity because they do not reflect the actual static and dynamic loads that may be imposed on tires, both during normal operating conditions and after the loss of one tire, especially if the tires are operated at their load rating and the requirements may not adequately account for tires that are operated at less than optimal conditions. And finally, 26, a cockpit image recorder would have helped determine the precise speeds at which the accident airplane traveled and the flight crew's responses to the anomaly, including flight and engine control inputs.
Thank you, Dr. Meyer. Is there any discussion?
Madam Chairman, I move that we adopt the findings as presented.
Second.
All in favor signal with a hand and aye. Aye. The ayes have it. The findings have been adopted. Dr. Meyer, will you read the probable cause?
The National Transportation Safety Board determines that the probable cause of this accident was the operator's inadequate maintenance of the airplane's tires, which resulted in multiple tire failures during takeoff roll due to severe underinflation, and the captain's execution of a rejected takeoff after V1, which was inconsistent with her training and standard operating procedures. Contributing to the accident were 1. Deficiencies in Learjet's design of and the Federal Aviation Administration's certification of the Learjet Model 60's thrust reverser system, which permitted the failure of critical systems in the wheel well area to result in uncommanded forward thrust that increased the severity of the accident. 2. The inadequacy of Learjet's safety analysis and the FAA's review of it, which failed to detect and correct the thrust reverser and wheel well design deficiencies after a 2001 uncommanded forward thrust accident. 3. Inadequate industry training standards for flight crews in tire failure scenarios. And 4. The flight crew's poor crew resource management.
Any discussion? Is there a motion?
So moved.
Second.
There's a motion to adopt the probable cause as presented in the staff draft report. All in favor signal with a hand and aye.
Aye.
Aye. The probable cause has been adopted. Dr. Meyer will now read the safety recommendations. If any board members have any questions or comments, please let me know when he has finished reading all of the recommendations.
The staff are proposing 14 recommendations to the Federal Aviation Administration. Number 1, provide pilots and maintenance personnel with information that 1, transport category aircraft tires can lose up to 5% pressure per day. 2, it may take only a few days for such tires to reach an underinflation level below what the aircraft maintenance manual specifies for tire replacement. And 3, the underinflation level that would require tire replacement is not visually detectable. 2, require that all 14 Code of Federal Regulations Part 121, 135, and 91 Subpart K operators perform tire pressure checks at a frequency that will ensure that the tires remain inflated to within aircraft maintenance manual specified inflation pressures. 3, require that aircraft maintenance manuals specify in a readily identifiable and standardized location required maintenance intervals for tire pressure checks as applicable to each aircraft. 4, allow pilots to perform tire pressure checks on aircraft regardless of whether the aircraft is operating under 14 Code of Federal Regulations Part 91, Part 91 Subpart K, or Part 135. 5, require tire pressure monitoring systems for all transport category airplanes. 6, identify the deficiencies in Learjet system safety analyses, both for the original Learjet 60 design and for the modifications after the 2001 accident that failed to properly assess the thrust reverser system design flaws related to this accident, and require Learjet to perform a system safety assessment for all other systems that also rely on air-ground signal integrity, and ensure that hazards resulting from a loss of signal integrity are appropriately mitigated to an acceptable level of safety risk. 7, revise available safety assessment guidance, such as Advisory Circular 25.1309-1A, for manufacturers to adequately address the deficiencies identified in the safety recommendation above, require that designated engineering representatives and their Federal Aviation Administration mentors are trained on this methodology, and modify FAA design oversight procedures to ensure that manufacturers are performing system safety analyses for all new or modified designs that effectively identify and properly mitigate hazards for all phases of flight, including foreseeable events during those phases, such as a rejected takeoff. 8, revise Federal Aviation Administration Order 8110.48 to require that the most current airworthiness regulations related to equipment, systems, and installations, 14 CFR 25.1309, are applied to all derivative design aircraft certificated as changed aeronautical products. 9, review the designs of existing derivative design aircraft that were certificated as changed aeronautical products against the requirements of the current revision of 14 CFR 25.1309 and require modifications of the equipment, systems, and installations to fully comply with this regulation. 10, define and codify minimum simulator fidelity requirements for tire failure scenarios. These requirements should include tire failure scenarios during takeoff that present the need for rapid evaluation and execution of procedures and provide realistic sound and motion cueing. 11, once the simulator model fidelity requirements requested in the safety recommendation above are implemented, require that simulator training for pilots who conduct turbojet operations include opportunities to practice responding to events other than engine failures occurring both near V1 and after V1, including but not limited to tire failures. 12, require that pilots who fly in 14 Code of Federal Regulations Part 135 operations in aircraft that require type rating to gain a minimum level of initial operating experience similar to that specified in 14 CFR 121.434, taking into consideration the unique characteristics of Part 135 operations. 13, require that pilots who fly in 14 CFR 135 operations in an aircraft that requires a type rating gain a minimum level of flight time in that aircraft type similar to that described in 14 CFR 121.434, taking into consideration the unique characteristics of Part 135 operations to obtain consolidation of knowledge and skills. And finally, 14, require that tire testing criteria reflect actual static and dynamic loads that may be imposed on tires both during normal operating conditions and after the loss of one tire, and consider less than optimal allowable tire conditions, including but not limited to the full range of allowable operating pressures and acceptable tread wear. That concludes the proposed new recommendations. Staff are proposing reclassifying 6 recommendations in this report. If you wish me to read them, I could do that now or I could do it later.
Go ahead.
As a result of this investigation, the NTSB issued 6 safety recommendations to the FAA on July 17, 2009. All of these recommendations have currently been classified as open response received, and this report is proposing to classify these recommendations. The first one is A0955, require Learjet to change the design of the Learjet 60 thrust reverser system in future manufactured airplanes so that the reverser lever positions in the cockpit match the positions of the thrust reverser mechanisms at the engines when the thrust reversers stow. This recommendation would be reclassified open acceptable response. A0956, once design changes are developed per safety recommendation A0955, require Learjet 60 operators to retrofit existing airplanes so that the reverse lever positions in the cockpit match the positions of the thrust reverser mechanisms at the engines when the thrust reversers stow. This would also be classified open acceptable response. A0957 reads, require Learjet to develop and install improved oral or visual cues on future manufactured Learjet 60 airplanes that would allow pilots to recognize an inadvertent thrust reverser stowage in a timely manner. This recommendation would be classified open acceptable response. And A0958, once improved oral and visual cues are developed per safety recommendation A0957, require Learjet 60 operators to install those cues on existing Learjet 60 airplanes. That recommendation would be classified also open acceptable response. A0959, require that all Learjet 60 pilots receive training for takeoff as well as landing phases of flight on recognizing an inadvertent thrust reverser stowage, including the possibility that the stowage can occur when the requirements for deploying thrust reversers are not fully met, such as when the air-ground sensor squat switch circuits are damaged. This recommendation would be classified acceptable alternate response. And finally, A0960, evaluate the design of the thrust reverser controls and indications in Raytheon Hawker 1000 business jets for potential thrust reverser failure modes that are similar to those identified in Learjet 60 airplanes and implement necessary changes. This last recommendation would be classified open acceptable response.
Thank you, Dr. Meyer. Is there any discussion?
I have a question regarding number 6, and I apologize for not noticing this sooner. And number 9, I expressed previously a concern in my meeting with the staff about the use of a standard of, quote, acceptable level of safety risk as being too imprecise for the purposes of recommendation, and you came up with a very good response to that, and you really tightened it down very well. I just happened to notice for the first time now that recommendation 6 also talks about on the new page 128, line 6, appropriately mitigated to, quote, an acceptable level of safety risk. And my question is that as easily tightened down as you did in 9? Because if not, I'll leave it alone. But I just raised that as it's a similar concern that for purposes of recommendation, that's a pretty soft standard, and I just wonder, is it possible to tighten that up? If not, I'll leave it alone. I'm just afraid that we get into arguments that they say, well, we did it, this is an acceptable level. We'd say, well, it isn't. And I'm just wondering, is there a more specific metric to use for that, like you did very well in recommendation number 9?
I think that same phrase from recommendation 9 would apply to recommendation 6 and could be added.
Mr. DeLacy, could you read what the revised recommendation would be? And go ahead and take a minute if you just need to.
Yeah, I apologize again for not noticing this sooner, but you did such a great job fixing it for number 9. I thought maybe it was doable as well for number 6.
Okay, thanks. We are ready. So number 6 would read, identify the deficiencies in the Learjet's system safety analyses for both the original Learjet 60 design and for the modifications after the 2001 accident that failed to properly address the thrust reverser system design flaws related to this accident, and require Learjet to perform a system safety assessment in accordance with 25.1309 for all other systems that also rely on air-ground signal integrity, and ensure that the hazards resulting from the loss of signal integrity are appropriately mitigated to fully comply with this regulation.
Vice Chairman, are you comfortable with that?
Yes, that's exactly the same solution you had for 9, and I think it works as well there too. Thank you.
Okay. Is there a motion to adopt the recommendation as revised?
So moved.
Second.
All in favor signal with a hand and aye.
Aye.
Aye. The ayes have it. Is there a motion to adopt the recommendations as revised? All of the recommendations.
So moved.
Second.
Signal with a hand and aye.
Aye.
Aye. The recommendations have been adopted as revised. Is there a motion to adopt the report as revised?
So moved.
Second.
All in favor signal with a hand and aye.
Aye.
The report has been adopted as revised. Are there any requests for concurring or dissenting statements? Seeing none, is there any other discussion or comments from the board members? Thank you to the staff for the excellent report and board meeting and for raising so many different issues. I think when we launched this accident, we certainly didn't expect to find all of these issues. This accident did not have to happen. The accident chain started with something as basic as tire underinflation and resulted in tragedy. As the Polish poet Stanislaw Lech wrote, "The weakest link in the chain is the strongest. It can break the chain." This accident illustrates all too clearly what can happen when one link in the chain breaks. This entirely avoidable crash should reinforce to everyone in the aviation community that there are no small maintenance items, because every time a plane takes off, lives are on the line. No one wants to be the weakest link. That is why we must have robust maintenance standards, rigorous design requirements, great training, and well-executed decisions in the cockpit. The captain in this accident was required to make a decision in an instant about whether to continue with the takeoff consistent with her training or to abort the takeoff after she had reached a speed at which she could not stop the plane on the remaining runway. That decision, made in the span of about 2 seconds, took her life and the lives of 3 others and left 2 others seriously injured. But she was not alone in rejecting a high-speed takeoff after passing V1. History has shown that others, experienced pilots among them, have made the same choice. The data shows us that over half of the rejected takeoff accidents and incidents occur after the airplane passes V1. Pilots are trained to avoid a rejected takeoff at high speed unless the aircraft cannot fly. But unfortunately, in a split second, pilots do not, and perhaps are not prepared to, accurately evaluate whether the aircraft cannot fly. Yet data cited in the Safety Board's 1990 Special Investigation Report on runway overruns following high-speed rejected takeoffs notes that out of 69 Boeing RTO events, in over half, the crews incorrectly interpreted the cause. High-speed rejected takeoffs are high risk, and they have catastrophic results. It is therefore not surprising that to reduce the risk of a rejected takeoff, pilots are trained in the go, no-go decision-making process. V1 marks the end of the go, no-go decision. If you have not applied the brakes by V1, you have made the go decision. Tragically, even though this is what we know and this is what is taught, in this accident, the high cost of this lesson was demonstrated again. Pilots must be prepared to make that difficult decision consistent with their training and not be fearful to commit, but they must have the training so they can do what they are taught to do. They must train like they fly and fly like they train. To quote Johann van Gogh, knowing is not enough, you must apply it. The FAA had information about Learjet 60 design deficiencies prior to this accident, yet it did not fully assess and incorporate that data into its certification process for changed aeronautical products. As we discussed today, neither the FAA nor Learjet adequately reviewed the Lear 60's design after an accident in Alabama in 2001 in which 2 people were seriously injured and the airplane was destroyed. While the modifications put into place after the 2001 accident provided additional protection against uncommanded forward thrust upon landing, no such protection was provided for a rejected takeoff. But whether the damage occurs on landing or takeoff, malfunctioning thrust reversers can be just as deadly. The data was there. It showed that there was a problem with the thrust reversers when there was a damage to a sensor on the landing gear. And additional data existed to demonstrate that tire failures were a common factor in RTOs. Yet the FAA and Learjet did not connect the dots. This accident investigation confirms what the Safety Board concluded in its 2006 study on the aircraft certification process. That is, if we are serious about safety, we must have programs in place to ensure the continued airworthiness of aircraft and assess the risks to safety-critical systems. An effective program can affect changes throughout the life of an aircraft and can ensure that ongoing decisions about design, operations, and maintenance and continued airworthiness consider new data, service history, lessons learned, and new knowledge. However, as this accident tragically demonstrates, FAA certification standards that allow grandfathering of derivative designs are in dire need of an overhaul. The Learjet 60 was certificated in 1993 based on some requirements that were in effect in 1965. That means that these standards were nearly 30 years old. A lot had been learned about airworthiness in 3 decades. Yet the FAA did not require the manufacturer to demonstrate that they had incorporated all of the new information into safety improvements. Had it done so in 1993 or perhaps in 2001, this accident may not have happened. This is particularly troubling because the industry had accepted a process for conducting this ongoing assessment in SAE ARP 5150. And in 2006, the Safety Board issued a safety recommendation, AO638, which is classified in unacceptable status, to require just such a program. The report adopted today concludes that had the FAA adopted the procedures described in the SAE's 5150 and required a program for the monitoring and ongoing assessment of safety critical systems, the FAA may have recognized, based on problems reported after previous incidents and accidents, that the Learjet 60's thrust reverser system design was deficient and thus may have required appropriate modifications before the accident occurred. If we're serious about safety, a dedicated program to continually monitor and assess risks is critical. This reminds me of a news article I read in the last week regarding recent safety recalls by Toyota in response to accounts of unintended acceleration. The article revealed that driver complaints about speed control problems were higher for Toyota than other big automakers, and that the pattern had been almost unbroken since 2004. Toyota and NHTSA both had the data, they just didn't see the problem until it was too late. Even if we have the data, we have to know what questions to ask. And unfortunately, unless we know what we're looking for, we may be looking for zebras when we really should be looking for horses. When we determine that the value of safety data is predictive, the problem will always be that we don't know what we don't know. The FAA and many others in the safety community believe that data programs are the way of the future. They might say that our findings from this one accident are not reflective of industry-wide problems. Yet we in the business of forensic accident investigations are compelled to ask, of what use is the data that is collected if it's not used to identify the right problems? Until we identify the problem, we cannot implement solutions. There's an old saying that says, what you don't know can't hurt you. When it comes to aviation safety, I suggest the opposite. What we don't know can hurt us. Whether through accident investigations or data programs, we must draw out the knowledge and we must share what we know, though it may be up to others to implement our recommendations. As you enter the doors of our training center in Ashburn, Virginia, you'll see the quote, "From tragedy, we draw knowledge to improve the safety of us all." At the Safety Board, we focus on lessons learned, recognizing that we can achieve safety improvements as a consequence of adversity. Sadly, there's one final thing that the data has borne out time and time again. Merely communicating is not enough. Communication has to be translated into action. If changes are not made as a result of our investigations, history is bound to repeat itself.